Have we finally discovered a real way to travel faster than light? Or have recent warp drive breakthroughs been misunderstood? Tonight, we'll examine what scientists have actually found, how space-time might be reshaped, and what still separates a mathematical possibility from a real starship. Before we begin, tell us where you're listening from tonight, and please like and subscribe to Sleepy Space for more quiet journeys through the universe. Before we imagine the ship, before we picture distant stars bending around its windows, and before the old dream of crossing the galaxy begins to feel almost possible, we should answer the question as honestly as science allows. No, we have not yet discovered a real way to travel faster than light. No spacecraft has done it, no laboratory has produced a working warp bubble, and no experiment has carried a person, an object, or even a chosen message beyond the boundary set by light. What researchers have discovered is quieter than a technological revolution, but still remarkable. They have found mathematical descriptions of space-time in which a journey could appear faster than light when viewed from far away, even though the traveler inside never races past a nearby beam of light. In these models, the ship does not win a contest of speed. Instead, the distance around it is altered. Space ahead is imagined as becoming shorter, while space behind becomes longer, carrying the ship inside a calm region like a leaf resting within a moving current. It is a beautiful idea, and it deserves to be taken seriously. But a beautiful idea is not yet a machine. A drawing of a bridge does not prove that the required steel exists, that the ground can support it, or that anyone knows how to build it. In the same way, a valid description of curved space-time does not automatically tell us what physical substance could create that curvature, how much energy would be required, how the structure could be controlled, or whether it would remain stable once the restless fields of the quantum world began to act upon it. This is where the meaning of the word real becomes important. A real method of faster-than-light travel would have to pass through several very different doors, and so far, none of the proposed ideas has passed through all of them. The first door is mathematics. The geometry must make sense within the laws being used to describe it. It cannot depend on a hidden contradiction, an undefined boundary, or a calculation that works only because an inconvenient part of the problem has been ignored. Some warp drive models do pass through this first door. They are not random fantasies written in scientific language. They are serious attempts to explore what Einstein's theory of gravity permits when space-time itself is allowed to bend, stretch, and evolve. The most famous example was proposed by physicist Miguel Alcubierre in 1994. He described a region of nearly calm, nearly flat space-time surrounded by a shell of strong curvature. A ship placed inside this region would not need to accelerate through space in the ordinary way. The region containing it could shift relative to distant stars, shortening the route ahead and lengthening the space left behind. To the passengers, the interior might feel peaceful. Their clocks would continue to tick. Their bodies would not necessarily endure the violent acceleration expected from an ordinary rocket. Yet to a distant observer, the bubble could cross a great distance in less time than a normal beam of light would need to travel through the unchanged space outside it. This was not a working design. It was a demonstration that the equations of general relativity contain stranger possibilities than everyday motion suggests. Alcubierre began by choosing the kind of geometry he wanted, and then asked what kind of matter and energy would be needed to support it. The answer led immediately to the second door: physical, material. Space-time does not curve simply because we describe it with elegant words. In general relativity, curvature must be connected to something physical: energy, mass, pressure, tension, or flows of momentum. A warp bubble would require these ingredients to be arranged in an extremely precise pattern around the ship. In the original model, important regions of the bubble appeared to require negative energy, meaning energy measured below the ordinary vacuum level by certain observers. This is not exactly the same as having less fuel in a tank, nor is it a substance we know how to scoop from empty space and store in a container. Quantum physics does allow small temporary situations in which energy can fall below a chosen vacuum reference, so negative energy is not entirely forbidden as a mathematical or microscopic phenomenon. But the known examples are limited, delicate, and surrounded by strict restrictions. They do not show that a civilization could gather enough negative energy to surround a spacecraft, hold it in the correct shape, and sustain it across interstellar distances. Some later studies have tried to reduce this difficulty. Researchers have explored smaller bubbles, different shell shapes, and configurations with positive total energy. Others have shown that certain warp-like arrangements moving below the speed of light may be supported without the same obvious need for exotic matter. These are meaningful advances because they help separate what is genuinely required by the equations from what was merely a feature of the earliest design. Yet, this is also where headlines can become misleading. A model described as a physical warp drive may still be only a theoretical spacetime with more realistic mathematical properties. The word physical may mean that its total mass is positive, that its matter shell behaves more normally, or that it satisfies particular energy tests. It does not mean that an engine has been built, that a material has been identified, or that faster-than-light motion has been achieved. In fact, some of the most promising recent models remain below the speed of light. They may resemble warp bubbles in their geometry, but they do not carry a ship beyond the causal boundary established by light. They are useful because they teach physicists how unusual gravitational structures might behave, not because they have already opened a road to another star. Beyond the problem of material lies the third door, creation and control. Imagine that somewhere in the future, a civilization discovers a form of matter capable of shaping spacetime in the required way. Even then, the hardest questions may only be beginning. How would the bubble be formed around the ship? How would the energy be placed in front of and behind it? How would the vessel accelerate, turn, or stop? Many mathematical models describe a bubble already moving at a steady speed, as though the most difficult part had happened before the story began. But a real machine must have a history. It must begin in ordinary space, change that space gradually, travel toward a destination, and return the surrounding geometry to a safe condition when the journey ends. Every stage must respect the conservation of energy and momentum. Every change must be communicated through the system. Every disturbance must avoid crushing the passengers or releasing dangerous radiation. A faster-than-light bubble may create regions around its boundary that signals from the ship cannot reach. The people inside could find themselves unable to influence the forward wall of the very structure carrying them. It would be like sailing inside a wave whose leading edge lies forever beyond the reach of the helm. Some analyses suggest that the route might need to be prepared in advance, which would weaken one of the greatest promises of a warp drive, the ability to depart freely for a destination not already connected by extraordinary infrastructure. Then comes the fourth door, the one that separates possibility from discovery more sharply than any other. Experiment. A genuine breakthrough would have to leave the pages of mathematics and produce a measurable effect in the world. Researchers would need to create controlled space-time curvature, identify its source, repeat the result, and show that matter or information had traveled in a way ordinary light could not match. No experiment has done this. No signal has been sent beyond its normal light boundary. No warp bubble has been detected around a spacecraft. No natural object has been confirmed as a vehicle using such a geometry. The absence of evidence does not prove that every imaginable faster-than-light method is impossible, especially because a complete theory uniting gravity with quantum physics has not yet been found. It does, however, tell us where the subject honestly stands. Faster-than-light travel is not a technology waiting only for a larger budget or a stronger engine. It is a deep theoretical question touching the foundations of space, time, energy, and cause. The recent progress is real, but the progress has been in learning how to ask the question more carefully. Physicists now distinguish between a ship moving through local space and a region of space changing globally. They distinguish between a coordinate on a diagram moving quickly and a physical object carrying information. They examine not only the energy seen by one convenient observer, but the energy measured from many possible states of motion. They ask whether a geometry can arise naturally, whether it can survive quantum effects, and whether its passengers could control it from inside. Each improvement makes the dream more precise, but precision can make an idea look more distant as often as it makes it look closer. A vague dream has no visible obstacles. A scientific model reveals every wall. And so our answer remains no. But it is not a cold or disappointing no. It is the answer found at the edge of an enormous landscape that has only begun to come into view. We have not discovered a real road faster than light, yet we have begun to understand what such a road would demand from the universe. It would require more than speed. It would require command over geometry itself, matter capable of producing extraordinary forms of curvature, a method for creating and steering that curvature, protection from instability and radiation, and a way to preserve the quiet order in which causes come before their effects. Somewhere far beyond the dark glass of our imagined ship, the stars remain separated by years of light, patient and almost motionless. The vessel has not begun to move. The bubble has not formed, but the question surrounding it has become clearer. And before we can understand whether distance might ever be folded, shortened, or carried like a wave, we must first understand why light is not simply the fastest traveler in the universe, but the boundary that gives every possible journey its shape. To understand why faster-than-light travel remains so elusive, we first have to release one of the simplest pictures the mind tends to create. The picture of light as merely the fastest runner in the universe, racing ahead of every ship, every planet, and every living thing because it happens to possess a greater speed. Light is fast, of course, unimaginably fast by human standards, crossing the distance from Earth to the Moon in a little more than a second and reaching us from the Sun in about 8 minutes. Yet its importance does not come from winning a contest. The speed of light is woven into the way space and time fit together, and this makes it less like a vehicle moving along a road and more like the quiet boundary that determines what a road can be. For centuries, the universe seemed to obey the gentle common sense of everyday motion. If a person walked toward the front of a moving ship, someone standing on the shore would see the person's walking speed added to the speed of the ship. If one carriage moved toward another, their closing speeds could be combined without mystery. This was the world described by classical mechanics, a world in which space formed a fixed stage, time passed at the same rate everywhere, and velocities could be added as naturally as distances on a map. Then, during the 19th century, the study of electricity and magnetism began to disturb that calm picture. James Clerk Maxwell showed that electric and magnetic fields were not separate curiosities, but two parts of one deeper structure, capable of traveling through empty space as waves. His equations predicted the speed of those waves, and the number matched the measured speed of light. Light, it turned out, was an electromagnetic wave. But the equations contained a troubling detail. They seemed to give light the same characteristic speed, without explaining whose motion that speed should be measured against. Sound has a speed relative to air. Waves on the sea have a speed relative to water. It appeared reasonable that light might also move through some invisible substance, and physicists gave that hypothetical medium a name: the ether. Earth, traveling through space, should have been moving through this ether like a ship through still water, and the motion should have changed the measured speed of light depending on the direction of the experiment. Yet increasingly careful measurements failed to reveal the expected effect. The famous Michelson-Morley experiment in 1887 was one of the clearest examples, though the history was more gradual and complicated than a single experiment overturning an entire world view overnight. What slowly emerged was the unsettling possibility that the difficulty did not lie in the instruments. The difficulty lay in the assumptions about space and time. In 1905, Albert Einstein approached the problem by treating two ideas as fundamental. The laws of physics should be the same for observers moving steadily relative to one another, and every such observer should measure the same speed for light traveling through empty space. These two ideas sound almost harmless when spoken quietly, but together they transform the architecture of reality. If two people moving relative to each other must both measure the same passing beam of light at the same speed, they cannot agree perfectly about the distance the light has crossed or the time it has taken. Something else must change. Clocks carried by moving travelers do not remain synchronized with clocks left behind. Lengths measured along the direction of motion do not remain identical for all observers. Events that appear simultaneous to one observer may occur at different times for another. These are not mistakes of vision caused by light taking time to reach the eye. They remain after all signal delays have been carefully corrected. They belong to the geometry of space-time itself. Space and time, once treated as separate and absolute, are joined into a single structure in which different observers divide the same reality into distances and durations in different ways. Beneath those disagreements, however, there remains a deeper quantity on which they all agree, a kind of space-time separation that combines distance and time into one invariant measure. This structure divides every event in the universe into regions of possible influence. Imagine a tiny flash occurring in the darkness. Light spreads outward from that event in every direction, forming an expanding sphere. If we include time as another direction in the picture, the expanding sphere traces the shape of a cone. Events inside the future cone can, in principle, be reached by something leaving the flash and moving at or below the speed of light. Events inside the past cone could have sent something that reached the flash. Events outside both cones lie too far away in space and too close in time for any ordinary signal to connect them. This light cone is not a wall made of matter. Nothing strikes it or bounces from it. It is a boundary of possibility, separating events that can share a cause and effect relationship from events that cannot be joined by known physical influences. Every object with mass travels along a path that remains inside its local light cone. It may drift gently, orbit a planet, fall toward a black hole, or be pushed by engines of extraordinary power, but its path remains on the slower side of that boundary. Light travels along the boundary itself. This is why the problem cannot be solved simply by building a more powerful rocket. The sound barrier once appeared intimidating, yet sound travels through a material medium, and an aircraft can exceed it, because the laws of mechanics do not treat the speed of sound as a fundamental division between different kinds of motion. The light barrier is different. As a massive object is pushed faster, each additional increase in speed requires more energy than the same increase required before. At ordinary speeds, the difference is so small that the older laws of motion work beautifully. As the object approaches the speed of light, however, the growth becomes severe. The ship can continue moving closer to the boundary, but every step becomes more expensive, and reaching the boundary would require an unlimited amount of energy. The ship's ordinary mass does not literally grow without end, as some older explanations suggested. Instead, its energy and momentum rise in a way that makes the final approach increasingly difficult. No finite engine, no matter how advanced, can complete that ordinary acceleration process and carry a massive ship smoothly through the light speed boundary. The mathematics does not describe a hidden region just beyond the limit that a sufficiently determined rocket can reach. It places slower-than-light matter and light like motion in different geometric classes. Hypothetical particles called tachyons were once proposed as entities that would always move faster than light. But such particles would not be normal matter accelerated beyond the limit. They would begin on the other side, following a fundamentally different kind of path, and no convincing experimental evidence has shown that they exist. There is also a beautiful difference in how time is experienced. A clock traveling with a massive object records what physicists call proper time, the time experienced along that object's own journey. As the traveler moves faster relative to someone left behind, the two clocks accumulate different amounts of time. The traveler does not feel their own clock slowing. Every heartbeat and thought remains ordinary from inside the ship. The difference becomes visible only when the travelers compare clocks again or exchange carefully analyzed signals. Light follows the boundary where the usual idea of elapsed proper time takes a special limiting form, though it is misleading to imagine what the universe looks like from the perspective of a photon, because light has no valid resting frame. A photon cannot be followed until it becomes stationary beside an observer. This absence of a rest frame is another sign that light is not simply ordinary matter moving very quickly. It belongs to the edge of the causal structure. Nature, nevertheless, produces many effects that seem to cross this boundary, and these apparent exceptions often become the source of exciting but misleading claims. The crest of a wave can sometimes move faster than light, because a crest is a repeating pattern rather than a single object carrying a message. The broad envelope of a pulse can appear to cross a strange material at a superluminal rate when different parts of the pulse are absorbed, delayed, and reshaped. But the earliest truly new information does not arrive before a light signal traveling through empty space could have reached the destination. In quantum tunneling experiments, a particle has a probability of appearing beyond a barrier that classical physics says it should not cross, and certain definitions of tunneling time can produce astonishingly short intervals. Yet these effects have not allowed researchers to send a controllable message outside the ordinary causal boundary. The emerging signal is shaped from components already present in the incoming quantum wave, and the part that could announce a genuinely new decision does not leap ahead of light. A laser beam swept across the moon can create a spot that appears to move across the surface faster than light, but the spot is not an object traveling from one lunar mountain to another. Each place is illuminated by different photons sent directly from Earth. No message is carried sideways by the moving point of brightness. Astronomers also observe jets of matter near distant black holes that appear to cross the sky at several times the speed of light. The effect arises because the material moves almost directly toward us at a speed close to light, causing light emitted at later moments to have less distance to travel before reaching Earth. The compressed arrival times create the appearance of impossible sideways motion, even though the plasma itself remains below the local limit. In water or glass, charged particles can even move faster than light travels through that material, producing the blue glow known as Cherenkov radiation. They do not exceed the speed of light in empty space. Light moves more slowly through matter because it interacts with the atoms and fields within the medium, while the deeper universal limit remains unchanged. Each of these examples teaches the same quiet caution. Not every measured or apparent speed represents a physical object or a freely chosen message crossing the causal boundary. Patterns can move strangely, Coordinates can behave strangely. Waves can be reshaped. Images can sweep across distant surfaces. But so far, every reliable test has preserved the deeper order. Massive objects remain inside their local light cones, and new information does not arrive outside them. For this reason, physicists sometimes describe the speed of light as the speed of causality. Light travels at that speed because photons have no rest mass, but the boundary would still matter even if no eyes had evolved to see light and no human language had ever named it. It governs the relationship between distance and duration, the behavior of energy and momentum, and the sequence by which one event can influence another. Yet this is not quite the end of the story, because everything described so far concerns local motion, what happens in a small region where spacetime can be treated as nearly flat. Einstein's later theory of gravity revealed that spacetime itself can curve and evolve. Distances between remote locations can change. Clocks can run differently in different gravitational environments. The universe as a whole can expand, carrying distant galaxies apart without those galaxies locally breaking the light speed limit. This leaves one narrow and remarkable question still open, not whether a ship can push harder until it overtakes a beam of light beside it, but whether the geometry between departure and destination can be changed so that the ship never needs to cross the forbidden boundary at all. And in the silence of that question, the familiar idea of speed begins to give way to something much deeper: the shape of the path itself. Once we understand that the speed of light is not merely the fastest speed anyone has measured, but the boundary that separates events able to influence one another from events that remain causally disconnected, the phrase "faster than light" begins to lose its apparent simplicity, because it can describe several very different things, and only one of them would truly carry a traveler beyond the limits of ordinary motion. Imagine a spacecraft drifting between two stars in perfect silence, its engines quiet, its passengers watching the darkness through a wide window. If a beam of light passes directly beside the ship, the most obvious meaning of faster-than-light travel would be for the spacecraft to overtake that beam in the small region of space they share. This is local motion, the speed that nearby instruments would actually measure, and it is the form of superluminal travel that established relativity does not allow for ordinary matter. No matter how a ship's journey appears on a distant map, every observer close to the ship should still see light move past at the same universal speed, while the ship itself remains slower. Curved space-time can change the shape of the route and alter the relationship between distant clocks, but it does not quietly remove this local rule. A spacecraft may approach the light speed boundary ever more closely, and its passengers may cross enormous distances while experiencing less time than people who remained behind. Yet they would still never watch a nearby photon fall behind their window through ordinary acceleration. This first meaning is therefore clear. A massive object directly outrunning local light has never been observed, and no accepted physical process is known to make it happen. The second meaning is far less dramatic, though it often creates dramatic headlines. A position written on a map can sometimes change faster than light, even when nothing physical is moving that way. The reason is that coordinates are not the universe itself. They are labels placed upon events, much as latitude and longitude are labels placed upon Earth. Near the poles, lines of longitude gather closely together, and a small physical movement can produce a surprisingly large numerical change in longitude. Nothing extraordinary has happened to the traveler. The grid has simply behaved in an unusual way. Space-time coordinates can do something similar. In the curved geometry around a black hole, for example, one choice of coordinates may make an object appear to slow almost to a halt near the horizon, while another coordinate system describes it crossing normally. The falling traveler does not experience two different realities. The descriptions differ because the maps divide space and time differently. A calculated coordinate speed can therefore rise above the speed of light without indicating that a body, message, or physical influence has crossed its local causal boundary. Even the coordinate speed assigned to light can vary in some descriptions of curved spacetime, while every nearby observer continues to measure the usual value. This is why physicists must look beyond a number printed beside a moving point. They ask what a clock beside the object would record, what a ruler placed nearby would measure, and whether information has actually reached an event that ordinary light could not reach. Without those questions, a strange coordinate system can be mistaken for a new law of nature. The third meaning is the one that gives warp drives their lasting fascination, because it does not require a ship to outrun light beside it. Instead, it asks whether the route between two distant places could be changed. Picture two villages separated by a high mountain. One traveler follows the long road around the slopes, while another walks slowly through a tunnel. The second traveler never moves faster, but arrives earlier because the path is shorter. General relativity allows space-time to have geometry, and that geometry determines the possible paths followed by matter and light. If a region of space-time could be reshaped so that the distance between departure and destination became shorter than the ordinary route, a traveler might arrive before a light signal sent through the unmodified space outside, even though the traveler remains slower than light at every local moment. This would be a genuine global shortcut. The ship would obey the rule in its immediate surroundings, while the larger geometry changed what destination could be reached and how soon. The universe already displays a natural example of why local speed and changing distance are not the same thing. On the largest scales, distant galaxies are carried apart by cosmic expansion. The farther a galaxy lies from us, the more rapidly the distance between us may increase, and beyond a certain scale, that rate of separation can exceed the speed of light. Yet astronomers do not interpret this as a galaxy firing engines and racing through its neighboring space at an impossible speed. The galaxy may remain nearly at rest relative to the matter around it, while the geometry separating distant regions evolves. Every nearby beam of light still behaves normally. The superluminal quantity belongs to the changing distance across a vast region, not to a local object overtaking light. This is often summarized by saying that space itself can expand faster than light, which is useful as a first picture, but the phrase should not be taken too literally. Space is not a hidden fabric blowing outward like smoke or water. What changes is the mathematical relationship used to measure separation between distant locations. The rulers imagined between the galaxies grow in a geometric sense, even though no single observer watches a physical ruler stretch past them at a superluminal speed. A warp drive tries to borrow the spirit of this idea and place it around a spacecraft. Instead of waiting for the entire universe to expand, the proposal imagines a controlled region in which the distance ahead becomes shorter while the distance behind becomes longer. The ship rests inside a comparatively calm interior, and the surrounding geometry carries that interior from one location to another. If this could be arranged, the passengers might never feel themselves crossing the local light barrier. They would simply find that the destination had been reached through a path that ordinary light traveling outside the altered region could not match. It is a graceful idea, almost like moving a boat by drawing the far shore closer rather than pushing the boat harder across the water. But the metaphor can conceal the real difficulty. The equations of gravity do not allow us to change distance merely by wishing for a shorter road. Geometry responds to matter and energy. A contraction in one region and an expansion in another must be supported by a particular arrangement of energy, pressure, tension, and motion. The ship may remain peaceful inside, yet the walls surrounding it could require physical conditions more extreme than anything found in ordinary engineering. The phrase, "the ship does not move faster than light, space moves instead," is therefore not a solution. It only identifies the type of loophole being explored. The next question is what must create that movement of geometry, whether the necessary source can exist, and whether the resulting spacetime can be formed and controlled without contradiction. A wormhole offers another version of the same global idea. Rather than carrying a bubble across the space between two stars, a wormhole would join two distant regions through a short internal passage. A traveler entering one mouth could move through the tunnel at a gentle speed and emerge far away before a beam of light following the long route through ordinary space could arrive. Again, the traveler would not locally outrun light. The geometry would provide a shortcut. But traversable wormholes face many of the same obstacles as warp bubbles. Their throats appear to require unusual forms of energy to remain open, and their stability under realistic disturbances is uncertain. If the two mouths move relative to one another or experience different gravitational histories, the wormhole may also disturb the ordinary order of time, turning a shortcut through space into a possible shortcut toward the past. This connection between global faster-than-light travel and causality is not an accidental philosophical complication added after the engineering. It arises from the structure of relativity itself. If two events are too widely separated for light to travel between them in the available time, different observers may disagree about which event happened first. As long as no signal can connect them, that disagreement causes no contradiction. But if a controlled shortcut allows a message to move between those events, and another shortcut returns the message through a differently moving frame, the reply may arrive before the original message was sent. A path that seems merely to cross space more quickly can therefore become a loop in time. This is why physicists define meaningful, faster-than-light travel through cause and effect rather than through the appearance of speed alone. A laser spot may sweep across the moon faster than light, but it cannot carry a message sideways across the lunar surface. A distant galaxy may recede at a rate greater than light, but no local observer sees it passing through neighboring space that way. A pulse may be reshaped so that its peak appears unusually early, but the genuinely new information does not escape the causal boundary. These examples are interesting, but they do not give a traveler access to a destination that lies outside the normal future reachable from departure. A true faster-than-light method would have to do exactly that. It would have to carry matter or a chosen message to a place and time that ordinary light, following the unaltered geometry, could not yet reach. Once the question is stated this carefully, the apparent loophole becomes far narrower. It is not enough to produce a large number called a speed. It is not enough to make a point cross a coordinate mat quickly. It is not enough to mention cosmic expansion or quantum strangeness. The proposal must change the actual causal relationship between departure and destination, and it must do so through a geometry supported by physically possible sources. It must also survive the effects of acceleration, radiation, quantum fields, and instability, while allowing the people inside to guide it and bring it safely to rest. So when we ask whether faster-than-light travel is possible, we are really asking three questions hidden inside one phrase. Can matter outrun nearby light? Established physics says ordinary matter cannot do so by ordinary acceleration. Can coordinates or distances change at an effective rate above the speed of light? Yes, such descriptions occur naturally, but they do not automatically transport anything beyond its causal boundary. Can space-time be shaped into a controlled shortcut that carries a traveler where ordinary light could not yet arrive? Mathematics offers geometries that suggest the possibility, but no known material, experiment, or engineering method has turned those geometries into a usable road. And now, with the meaning of the question finally clear, we can approach the proposal that gave this dream its most famous form. A quiet interior carried through the universe inside a wave of curved space-time, where the ship does not race across the distance, because the distance itself has been asked to change. In 1994, A physicist named Miguel Alcubierre asked a question that sounded almost like something whispered from the edge of science fiction. If a spacecraft could never accelerate through its local surroundings faster than light, could the surroundings themselves be arranged so that the ship reached a distant place without ever breaking that local rule? His answer was not an engine, not a machine, and not a claim that such a journey could be built, but a carefully constructed geometry inside Einstein's theory of gravity, a mathematical spacetime shaped around a quiet central region in which a spacecraft might rest, while the distance ahead contracted and the distance behind expanded. The image is simple enough to hold in the mind as the night grows still. Picture a small boat floating on a dark ocean. The boat's motor is silent. It does not cut violently through the water. Instead, a broad wave forms beneath it, lifting and carrying the boat forward, while the water itself moves. The Alcubierre idea replaces water with spacetime, although the comparison must remain only a guide, because spacetime is not a material ocean flowing around solid objects. It is the geometry that determines how distances are measured, how clocks compare, and how matter and light move from one event to another. In the proposed geometry, the ship would sit inside a bubble whose interior could remain nearly flat, meaning that the immediate environment around the passengers might resemble ordinary empty space. The strongest curvature would be concentrated in a surrounding wall, a shell separating the calm interior from the distant universe. Ahead of the bubble, distances would be reduced. Behind it, distances would increase. From far away, the bubble could appear to move across space, perhaps even crossing a distance faster than an ordinary beam of light could cross the unchanged region outside it, while the ship inside continued to follow a slower-than-light path in its own local neighborhood. This distinction is the heart of the proposal. Alcubierre did not describe a vessel forcing its way through the light barrier. He described a path in which the barrier was never crossed locally because the geometry carrying the vessel had changed. A nearby photon would still pass the ship at the normal speed of light. A clock aboard the craft would still tick in the usual way. The passengers would not necessarily feel the crushing acceleration that an ordinary rocket would experience if it tried to gain speed rapidly. To them, the voyage might feel strangely uneventful, a room floating inside a moving shape of spacetime, while outside, stars that once lay years away slowly drew nearer. It is this peaceful interior that makes the idea so captivating. Human beings are accustomed to paying for motion with force. Cars push against roads, aircraft push against air, rockets throw exhaust backward, and every rapid change in velocity presses against the body. The Alcubierre bubble seems to offer movement without that familiar violence, because the vessel is not being pushed across its local space in the ordinary sense. Yet the absence of force inside the bubble does not mean the geometry is effortless. The calm at the center is purchased by extreme conditions in the surrounding wall, just as the quiet eye of a storm can exist only because powerful motion surrounds it. To understand why, it helps to remember how Alcubierre approached the problem. In most physical calculations, researchers begin with a known source of matter or energy and then calculate how it affects the world around it. Given a star, they determine how space-time curves nearby. Given a moving electric charge, they determine the electromagnetic field it produces. Alcubierre reversed this direction. He first imagined the geometry that would produce the desired journey, then inserted that geometry into Einstein's equations to discover what kind of matter and energy would be required to support it. This is called working backward from a metric, the mathematical description of distance and time in a given spacetime. It is a valid method for exploring what the equations allow, but it carries an important warning. Choosing a geometry is not the same as discovering a physical process capable of creating it. A person can draw the exact shape of an arch and calculate the pressure at every point, yet still discover that no available stone can bear the load. In the warp bubble, the required source turned out to be deeply unusual. Some observers near the wall would measure regions of negative energy density, a condition unlike the behavior of ordinary matter gathered into planets, stars, fuel tanks, or laboratory materials. The problem was not merely that the energy requirement seemed enormous, although early estimates were indeed extraordinary. The greater difficulty was the form the energy had to take. It needed to be arranged around the bubble with precise changes in pressure, tension, and momentum, creating the contraction in front and expansion behind without filling the interior with equally severe curvature. This made the warp drive less like a powerful rocket and more like an instrument capable of sculpting the gravitational structure of empty space. Over the years, physicists explored ways to reduce the apparent cost. Different bubble shapes were proposed. The wall could be made thinner or distributed differently. The size of the calm interior could be altered. Some models suggested that the total amount of negative energy might be lowered dramatically compared with the earliest estimates, although such reductions often introduced new difficulties, such as extremely thin shells or regions where the curvature became even more intense. This is a recurring pattern in theoretical physics. A problem removed from one part of a model may reappear in another, not because researchers have failed, but because the equations quietly preserve the underlying cost. A smaller amount of exotic energy may need to be concentrated with impossible precision. A smoother interior may require harsher conditions in the wall. A configuration that looks manageable while moving steadily may become difficult when asked to start or stop. The geometry can be reshaped, but the physical burden does not simply vanish. There is also a subtle question hidden inside the phrase, "the bubble moves." In Alcubierre's original construction, the position of the bubble is described as a function chosen in advance. One can specify where its center is at each moment, almost as though the universe has already been told the route and timetable. This is useful for studying the space-time, but it is not yet a propulsion law. It does not explain which engine changes the bubble's motion, what force acts on the shell, or how the required energy rearranges itself when the craft turns. The mathematical geometry can describe a bubble crossing space at a chosen rate without identifying a physical control system that makes the journey happen. In this sense, the proposal resembles a film of a wave already moving across an ocean, while the camera begins after the wind has risen and before anyone asks what created the wave. A real voyage would require the entire story. The bubble would have to emerge from ordinary space-time. The necessary fields would have to form around a ship without destroying it. The structure would have to gain motion, maintain its shape, respond to navigation, and finally dissolve at the destination. Each stage would produce changing gravitational fields, and changing gravitational fields can carry energy away as radiation. The passengers would also need some means of communicating with the bubble wall, yet a superluminal configuration may create horizons that divide the interior from parts of its own boundary. Light sent forward from the center might never reach the leading edge, because that region would be moving away, through the geometry, faster than the signal could catch it. The craft could become like a vessel whose rudder lies beyond the reach of every command sent from the bridge. This raises the possibility that the bubble's path would need to be prepared from outside or established before departure, which would turn a seemingly free method of exploration into something more like a cosmic railway built along the entire route in advance. Another concern waits at the front wall. As the bubble moves, particles and light already present in space could interact with the surrounding curvature. Some analyses suggest that radiation might accumulate or become strongly shifted in energy near parts of the bubble, potentially producing a dangerous release when the structure slows or collapses. The details depend on the exact model and remain an area of study. So these outcomes should not be treated as identical for every possible warp geometry. Still, they reveal why a peaceful cabin does not guarantee a safe journey. The most violent effects may remain outside the passenger's immediate view until the moment the bubble changes. Even the meaning of speed becomes strange inside such a construction. The ship is not crossing neighboring points of space in the manner of a rocket. Instead, a whole region containing the ship is embedded in a changing geometry. From the passenger's local point of view, nothing exceeds light. From the distant point of view, the center of the bubble may cover a separation in less time than an external light signal. Both statements can be true because they describe different aspects of the same space-time. This is why the Alcubierre proposal is more than a clever trick of language. It demonstrates that general relativity distinguishes sharply between local motion and global travel time. It shows that Einstein's speed limit, firm as it is, does not by itself settle every question about distant journeys in curved spacetime. Yet it also shows that the apparent loophole is guarded by deeper laws. The equations may permit the shape, but they reveal an extraordinary source. The interior may be calm, but the wall may be exotic. The route may be written, but the mechanism remains absent. The bubble may move in the model, but no one inside has yet been shown how to steer it. This is the enduring value of Alcubierre's work. It did not bring humanity closer to a star by a measurable number of miles, but it transformed a vague dream into a question that physics could examine. Before 1994, warp travel belonged mostly to storytelling, where space bent because the plot required it. Afterward, researchers could ask exactly what kind of curvature would be needed, what energy conditions would be violated, how horizons might form, and whether later geometries could reduce the cost. A fantasy had been given a mathematical body, and once it had a body, every weakness could be located. The bubble now hangs before us in the darkness, almost perfectly quiet at its center, its passengers untouched by impossible speed, while around them the wall carries the full weight of the journey. Nothing in the cabin reveals how strange the surrounding space-time has become. A cup rests on a table. A clock advances 1 second at a time. Beyond the window, the destination seems to approach without the ship ever feeling that it has raced toward it. But hidden in the curved shell are the unanswered demands of matter, energy, control, and causality. And to understand whether this beautiful geometry could ever exist outside an equation, we must move closer to that wall and ask what kind of physical substance could possibly bend space-time into such a shape. The quiet interior of a warp bubble can make the journey seem almost effortless, but the stillness at its center hides the true price of the voyage. Because in general relativity, space-time does not bend without a physical reason. Every curve in the geometry must correspond to some arrangement of energy, pressure, tension, or momentum, and the wall surrounding an Alcubierre bubble would need all of these ingredients, organized with a precision far beyond anything ordinary engineering has ever attempted. This is the point where the dream of changing distance becomes a question about matter itself. A star curves space-time because it contains mass and energy. A planet creates a gentler curvature for the same reason. Even light contributes to gravity because it carries energy and momentum. But a warp bubble would require more than a large amount of ordinary mass placed near a spacecraft. The energy would have to be distributed in a very particular pattern, strong enough to produce contraction in front of the ship and expansion behind it, while somehow leaving the interior calm enough for passengers to survive. The difficulty is therefore not simply the size of the fuel tank, it is the nature, shape, and behavior of the source. Einstein's equations connect the geometry of spacetime to what physicists call the stress-energy content of matter, a name that sounds technical but describes several familiar ideas gathered into one structure. It includes energy density, which tells us how much energy is present in a region, but it also includes pressure, tension, the flow of energy, and the movement of momentum from one direction to another. In ordinary life, pressure and tension seem less fundamental than mass, yet in relativity they also contribute to gravity. A compressed fluid, a stretched field, or a beam of radiation can alter spacetime because gravity responds not only to what matter is, but also to how matter moves and how it pushes against its surroundings. A warp bubble would demand an extraordinary pattern of all these effects. The wall could not be created by placing a heavy ring around a ship and simply switching it on. Its stresses would need to vary from point to point, changing across the front, sides, and rear of the bubble in precisely the right way. The original Alcubierre geometry revealed that some observers near the wall would measure negative energy density. This phrase often creates confusion because it sounds like energy has somehow become less than nothing. But the idea is more subtle. In classical physics, the energy density of ordinary matter is usually positive. A stone, a cloud of gas, or a beam of light adds energy to the region it occupies. Negative energy density means that, relative to a chosen vacuum state, a region behaves as though it contains less energy than empty space would normally possess. Such a condition is unusual. But quantum physics does not rule it out in every circumstance. The vacuum is not truly empty. It is the lowest energy state of fields that continue to fluctuate even in darkness. And under carefully arranged conditions, those fields can produce local regions whose energy density falls below the surrounding vacuum level. The Casimir effect is often mentioned as an example. When two conducting plates are placed extremely close together, the allowed quantum fluctuations between them differ from those outside, creating a measurable force. This experiment is real and well established, but it does not provide a container filled with useful negative energy. The effect is tiny, highly constrained, and dependent on the entire arrangement of fields and boundaries. It cannot simply be scooped from the vacuum, stored in a tank, and released around a starship. The difference is similar to observing a slight depression in the surface of the sea and concluding that one has discovered an endless supply of water below sea level. The depression is real, but it exists only as part of a wider pattern, surrounded and balanced by the rest of the ocean. Quantum theory also appears to place strong restrictions on how much negative energy can exist, how long it can remain, and how widely it can be spread. These restrictions are often described through quantum inequalities. Their detailed form depends on the field, the observer, and the geometry, but their general message is clear. The more negative the energy becomes, the more briefly it tends to be available, and attempts to sustain it are usually accompanied by compensating positive energy. Nature seems to permit small loans below the vacuum level, but not an unlimited account that can remain open forever. For a macroscopic warp bubble, this is a severe obstacle. A shell surrounding a spacecraft might need negative energy across a region many meters wide, maintained for the entire voyage, with a shape stable enough to preserve the calm interior. Known quantum effects operate on much smaller scales and do not show how such a structure could be built. Early estimates of the total energy required for an Alcubierre bubble were staggering, in some cases exceeding the mass energy of planets or stars, depending on the size and shape assumed. Later researchers found ways to reduce those numbers by altering the geometry. A smaller bubble could reduce the volume of the wall. A thinner wall could concentrate the curvature into less space. Alternative shapes could redistribute the most extreme regions. These changes were valuable because they showed that the original estimates were not universal. Yet lowering the total amount of energy did not automatically make the system realistic. When the wall becomes thinner, the energy may need to be compressed into an increasingly narrow layer. When the layer becomes too narrow, the curvature can grow violently, and the required precision may approach scales where classical relativity is no longer trustworthy. A solution can therefore become cheaper in total energy while becoming more difficult in density, stability, or control. It is like reducing the amount of material in a bridge by making every support thinner until the entire structure depends on fibers no known substance can produce. The cost has not disappeared. It has changed its form. This pattern appears again in modified warp geometries. Some designs replace the simple spherical bubble with more complicated shells. Others shrink the passenger region while keeping the exterior displacement large. Some aim to produce positive total mass even though negative regions remain locally. A positive total mass is important because it makes the entire space-time resemble an ordinary gravitating system when viewed from far away. But it does not prove that every part of the structure can be made from ordinary matter. A mixture of large positive and negative contributions can still add up to a positive result. In the same way, a bank account may end the day above zero, even if it depended on transactions that no real bank would permit. Researchers must therefore examine not only the total energy, but also what every possible observer would measure while passing through the geometry. This is where the energy conditions enter the story. They are not substances or forces, but general tests used in relativity to describe matter that behaves in broadly familiar ways. One version asks whether any ordinary observer moving through a region would measure a non-negative local energy density. Another asks whether light, like rays, encounter a pattern of energy that focuses them as normal gravity usually does. These conditions support many important results in gravitational physics, including theorems about black holes, singularities, and causal structure. They are not sacred rules that quantum theory must obey in every microscopic circumstance, yet violating them on a large and sustained scale often signals that the proposed matter is unlike anything known. The original Alcubierre bubble violates important energy conditions near its wall. More general analyses have suggested that genuine space-time shortcuts often require similar violations, not merely because one particular metric was poorly chosen, but because ordinary positive energy tends to focus paths rather than open shortcuts between distant regions. Gravity generated by conventional matter usually draws neighboring paths together. A warp shortcut must create a more unusual pattern, allowing some routes through space-time to become earlier or shorter than the paths light would otherwise follow. This does not prove that every conceivable theory of quantum gravity forbids such a structure, but it explains why negative or exotic energy returns so persistently in warp drives and traversable wormholes. It may be connected to the very function of the shortcut rather than to the details of one design. There have been proposals claiming that superluminal warp-like solutions might be supported by positive energy, and these ideas deserve careful study because they explore parts of Einstein's equations that earlier models did not. Yet the phrase positive energy must be used cautiously. Energy density depends on the motion of the observer. A person moving with one part of the geometry may measure a positive value, while another observer passing through at a different speed or direction may measure something else. To say that a model avoids exotic matter, researchers must test the full stress-energy structure, not only the value seen in one convenient frame. Some proposed positive energy solutions have later been re-examined under broader tests, with critics arguing that violations remain when more possible observers are considered. This scientific disagreement is not a sign that the entire subject is meaningless. It shows how difficult it is to translate a mathematical source into a physically acceptable material. The equations may allow a tensor to be written down, but nature must still provide fields capable of producing that tensor without instability, contradiction, or hidden negative regions. There is also the question of scale. Human beings have learned to create small curvatures in spacetime simply by moving masses, and every object in a laboratory produces gravity, though far too weak to notice without sensitive instruments. We can generate intense electromagnetic fields, high pressures, and brief concentrations of energy. We can even observe quantum states with unusual local properties. But a warp bubble would require control over gravity itself at a level that makes present technology seem almost untouched by the problem. Gravity is extraordinarily weak compared with the other known interactions at ordinary scales. To create noticeable curvature in a compact region usually requires enormous mass or energy. A planet bends spacetime gently because it contains an almost unimaginable number of particles. A neutron star bends it strongly because the mass of a star is compressed into a sphere the size of a city. A black hole produces even more extreme geometry because enough energy has collapsed within a critical region. A warp drive would need strong, delicately shaped curvature without trapping the ship inside a black hole or tearing the bubble apart. It would have to create not merely a deep gravitational well, but an asymmetric moving pattern, one that remains smooth, navigable, and reversible. This is a far more demanding task than producing a strong gravitational field. It is the difference between creating a storm and shaping every current within it so precisely that a quiet room can travel inside. Even if a future theory reveals new states of matter, the energy problem will remain connected to engineering. The source must be generated, held in place, and rearranged as the bubble moves. If the geometry changes direction, the stresses in the wall must change with it. If the bubble accelerates, energy and momentum must be exchanged with the surroundings. If the structure collapses, the stored energy must go somewhere. A design that requires only a small amount of exotic material may still fail if that material cannot be stabilized or moved. A design with positive energy may still be impossible if the pressure or tension exceeds any physically realizable limit. The deepest question is therefore not whether negative energy exists in some narrow quantum sense, but whether the complete pattern demanded by a warp bubble can exist as a stable, controllable system in nature. At present, there is no evidence that it can. Yet the search has not been empty. By studying these extreme geometries, physicists have learned more about the relationship between gravity and quantum fields, about the limits of energy conditions, and about the difference between a space-time that can be described and one that can be produced. The warp bubble acts like a lantern carried toward the boundary of our theories, revealing where general relativity remains flexible and where quantum physics begins to resist. In the calm center of our imagined vessel, the passengers might still feel nothing unusual. The floor would remain beneath their feet, their breathing would be slow. The destination would hang somewhere ahead in the darkness. But around them, hidden beyond the quiet cabin, the wall would need to contain a pattern of energy stranger than any fuel humanity has ever used, a pattern balanced between curvature and collapse, between mathematical permission and physical reality. And as we look more closely at that wall, another question begins to emerge. Perhaps the requirement for negative energy can be softened. Perhaps different geometries can be supported by more ordinary matter. And perhaps the most recent models have found a way around the oldest obstacle. But before we allow that hope to carry us too far, we must ask what those newer claims of positive energy warp drives actually mean. For many years, the need for negative energy seemed to place the warp drive behind a wall that no known technology could approach. And so, when researchers began publishing models described as positive energy warp drives, the words carried an almost irresistible promise, as though the oldest obstacle had finally been removed and the silent ship at the center of our story might soon be given a material body. But scientific language often contains distinctions that disappear when compressed into a headline. And in this case, the difference between finding positive energy somewhere in a model and proving that the entire model can be built from ordinary matter is the difference between opening a small window and discovering an open road. To understand what these newer studies really changed, we must move carefully, because they were not empty exercises, nor were they completed designs. They expanded the mathematical landscape, revealed assumptions hidden inside the original Alcubierre geometry, and showed that some structures resembling warp bubbles may be less exotic than once believed, especially when they remain below the speed of light. Yet none has demonstrated that a controllable superluminal bubble can be formed from familiar matter. One of the most widely discussed proposals appeared in 2021, when physicist Eric Lentz described a family of soliton-like solutions in general relativity. A soliton is a stable traveling pattern, something like a wave that preserves its shape while moving, and such structures appear in many areas of physics, from fluids to optical fibers. In the Lentz proposal, the moving region of spacetime was designed so that its energy density appeared positive when measured by a particular family of observers. This mattered because the original Alcubierre bubble required negative energy near its wall, and any credible route away from that requirement would represent real theoretical progress. The proposed geometry also suggested that electromagnetic fields and a kind of conducting plasma might, at least in the mathematical description, contribute to the required source. It was tempting to imagine that the mysterious substance surrounding the ship had been replaced by fields and matter that already belonged to known physics. But the full question was more demanding than whether one observer found a positive number. Energy in relativity is not measured in exactly the same way by every observer. A person moving alongside a system may divide its energy, momentum, and pressure differently from someone crossing it in another direction or at another speed. The complete physical source contains all these quantities together, and a model can appear ordinary in one frame while revealing unusual behavior in another. This is why physicists use energy conditions. They ask whether every physically reasonable observer passing through a region would measure an acceptable energy density, and whether light moving through the geometry would be focused or defocused in the way ordinary matter generally causes. To show that exotic matter has truly been removed, it is not enough to choose the observer who sees the most favorable result. The geometry must pass the broader test. Later analyses argued that when a wider range of observers was considered, negative regions or related violations remained in the lens construction. This did not make the original work worthless. On the contrary, it exposed how subtle the phrase positive energy really is, and encouraged researchers to develop more complete ways of testing warp geometries. Science often advances in this manner, not through a single perfect answer, but through a proposal precise enough that its weaknesses can finally be measured. Around the same time, Alexei Bobrik and Gianni Martire introduced a more general framework for understanding warp drives. Rather than treating the Alcubierre bubble as one unique object, they examined a broad family of spacetimes containing an interior region surrounded by a moving shell. Their work clarified that the calm region inside a warp bubble does not automatically propel itself. The material shell must still possess motion, energy, and momentum. In other words, a warp drive is not a reactionless engine merely because the passengers feel little acceleration. Something physical must carry the structure, and changing its motion still requires a transfer of momentum. This correction is quiet but important. Popular images often show the bubble as though curved spacetime itself has replaced every need for propulsion. Yet the geometry does not erase conservation laws. If the shell accelerates, turns, or stops, there must be an explanation for the energy exchanged during that change. Bobrick and Martier also showed that warp-like bubbles moving below the speed of light can, in principle, be supported by positive energy matter. Such configurations may contain a flat or nearly flat interior carried inside a gravitating shell without demanding the negative energy of the original superluminal design. This means that the general idea of transporting a region of spacetime is not automatically forbidden. A massive shell with ordinary energy can create curvature, and that curvature can be shaped into something that resembles a warp bubble. But if the entire system remains below light speed, it has not solved the central problem of our journey. It may offer a new way to think about gravitational propulsion, inertial environments, or engineered spacetime, but it does not deliver a traveler to a destination before ordinary light could arrive. The distinction between sublight and superluminal warp drives is therefore not a matter of degree, like comparing a slow airplane with a fast one. It marks a deeper transition in causal structure. Below the light boundary, signals from the center can still influence the surrounding shell in the ordinary way, and the system can remain connected by normal cause and effect. Above it, horizons may form. Energy conditions become more difficult to satisfy, and the geometry begins to threaten the usual ordering of events. A model that works peacefully on the slower side cannot simply be pushed a little harder and expected to cross into the faster side unchanged. The equations may demand an entirely different source once that boundary is crossed. This is one reason the positive energy results must be described with both respect and restraint. They show that some warp geometries are compatible with less exotic matter, but they do not show that a true faster-than-light shortcut can be built in the same way. A more recent line of research has continued this careful separation. In 2024, researchers presented a constant velocity physical warp drive solution consisting of a stable matter shell combined with a particular distribution of space-time shift. The system was constructed to move below the speed of light and was reported to satisfy the energy conditions examined in the analysis. The result was valuable because it provided a clearer numerical example of a warp-like region with positive total mass and physically better behaved matter. It demonstrated that the vocabulary of warp drives need not belong only to impossible superluminal bubbles. General relativity may permit unusual moving shells and protected interiors without violating the most basic properties expected of matter. Yet the same feature that made the model more physically reasonable also kept it from answering the title's question. It remained sublight. It did not carry information outside a light cone. It did not create a shortcut that allowed arrival before an ordinary beam of light. It also described motion at a steady speed, rather than offering a complete engine capable of beginning from rest, accelerating, steering, and stopping. This reveals another difficulty hidden inside the word solution. In mathematics, a solution may describe a configuration that satisfies the equations at every point. In engineering, a solution must also explain how the configuration is produced, how it responds to disturbances, how it is controlled, and what happens when conditions change. A perfectly described bridge floating in the air is not yet a bridge anyone can build if the method of raising it remains unknown. The same is true of a steady warp shell. The existence of the completed geometry does not provide the history that creates it. Researchers have also explored new shapes for the surrounding source. Instead of one continuous ring or shell, some geometries divide the required stresses into separate cylindrical regions, sometimes described as nacelles, arranged around a flatter passenger volume. The word naturally recalls the engine structures attached to fictional starships, and the geometry does appear more modular than the original bubble. By changing the number, placement, and shape of these regions, physicists can study how curvature, pressure, and energy are distributed, and whether the interior remains flat enough for passengers. This is a useful development in mathematical design because it allows the geometry to be adjusted in more controlled ways. But a modular drawing does not mean that modules can be manufactured. The required stresses may still be exotic in important regions, and no known material can yet be arranged to reproduce them. A diagram can begin to look like engineering long before nature has provided the components. Behind all these proposals lies a general problem. Ordinary matter creates gravity, but ordinary positive energy tends to focus the paths of light. A true spacetime shortcut asks the geometry to do something more unusual, allowing a traveler to reach a distant region earlier than the normal light paths through the surrounding space. Under broad assumptions, this often requires the light paths to be defocused or rearranged in ways associated with violations of familiar energy conditions. This does not amount to a final proof against every future theory, because general relativity may not be the last description of gravity, and quantum effects can violate classical conditions in limited circumstances. But it explains why the problem returns even when the bubble is redesigned. The obstacle may not belong only to Alcubierre's chosen shape. It may be tied to the very act of creating a superluminal shortcut. If so, changing the shell can reduce the cost without eliminating the deeper requirement. There is also a danger in thinking of positive energy as automatically safe or practical. A model may use no negative density and still require an impossible amount of ordinary energy. It may demand pressures greater than those inside neutron stars, tensions no material could survive, or gradients so sharp that tiny errors would destroy the intended geometry. A star contains positive energy, yet no engineer can gather a star around a spacecraft and shape its gravity into a moving shell. A black hole also has positive mass, but this does not make it a useful or gentle engine. The sign of the energy is only one part of the question. Its amount, distribution, motion, stability, and controllability matter just as much. Even a positive energy warp bubble would have to avoid collapsing under its own gravity, avoid forming unwanted horizons, and protect the passengers from tidal forces and radiation. It would need a source capable of changing shape as the vessel turns, because a fixed pattern of curvature would carry the ship only along a predetermined path. It would need a way to exchange momentum with the environment, because the laws of physics do not allow the complete system to accelerate for free. And it would need to survive contact with the quantum vacuum, whose fluctuations may respond violently near horizons or strongly curved walls. So what have the positive energy models truly achieved? They have shown that the phrase warp drive covers more than one geometry. They have demonstrated that a calm interior, surrounded by a moving gravitational shell, is not necessarily dependent on negative energy when the motion remains below light speed. They have clarified that the shell is a physical object with mass and momentum, rather than a magical wave detached from conservation laws. They have forced researchers to test energy conditions for many observers instead of trusting one preferred viewpoint. And they have offered better numerical tools for exploring how unusual spacetimes behave. These are meaningful advances, but they move us toward a clearer theory, not toward a finished starship. The silent vessel remains in the center of our imagined bubble, and for a moment the wall around it appears less mysterious. Some parts may be described with positive energy. Some slower versions may even resemble matter allowed by familiar physics. Yet when we ask the wall to carry the ship faster than light, the old shadows return. Hidden negative regions, extreme pressures, causal horizons, and sources no laboratory can produce. The newest models have not erased the barrier. They have illuminated its shape. And now, to understand whether the recent excitement represents a genuine turning point or only a more refined map of the same forbidden coast, we must examine exactly what the latest warp drive studies have discovered, what they carefully avoid claiming, and why the most physically realistic examples still remain on the slower side of light. The most recent warp drive studies have not given humanity a machine capable of outrunning light, but they have changed the question in a quieter and more useful way, replacing some of the older, almost mythical language with models that can be tested more carefully, compared more honestly, and separated into what may be physically reasonable and what still belongs to the far edge of theory. The first major step in this newer phase came in 2024, when a group of researchers presented what they called a constant velocity physical warp drive solution. The name sounded dramatic, but the most important word in the paper was not warp. It was subluminal. The proposed structure remained below the speed of light. It combined a shell of positive mass with a controlled distortion of space-time, creating a calm interior region and a surrounding geometry that resembled features of earlier warp bubbles. Unlike the original Alcubierre model, the numerical solution was designed to satisfy the energy conditions examined by the authors, meaning that it did not obviously require the same negative energy regions that had haunted the earliest proposals. This was a serious achievement because it showed that a moving shell of curved spacetime carrying a protected interior does not automatically require exotic matter when it remains on the slower side of light. Yet the model did not provide faster-than-light travel, and the paper did not claim that it did. It described a bubble moving at a constant speed, already formed and already in motion, without explaining how a ship would create the shell, accelerate it from rest, guide it across space, or bring it safely to a stop. The geometry was more physical than many older examples, but it was not an engine. It was closer to a carefully drawn current in a mathematical ocean, one that could carry a quiet region along with it, while leaving unanswered where the current came from and what machinery sustained it. This distinction matters because scientific progress does not always arrive as a sudden door opening. Sometimes it arrives as a wall becoming more clearly measured. The 2024 solution narrowed the problem by showing that the idea of a warp-like shell should not be rejected simply because the word warp appears in its name. Some versions may be compatible with ordinary positive energy. Some may preserve a flat interior. Some may be treated as gravitating objects rather than impossible fantasies. But the same result also made the true faster-than-light problem stand out more sharply, because once the exotic features were removed, the motion remained below light speed. The geometry became more believable precisely where the extraordinary promise disappeared. In late 2025, another study offered a different kind of improvement, changing not the speed of the bubble, but the architecture of its surrounding wall. The original Alcubierre model placed the unusual energy around the ship in a continuous ring-like distribution. The newer proposal divided that distribution into separate cylindrical regions arranged around a flat interior, and the researchers called these regions nacelles, borrowing a word from aviation and spacecraft design. Two nacelles could sit on opposite sides of the passenger region, while 3 or 4 could form other symmetrical arrangements. To the imagination, the picture looked far more like a constructed spacecraft than a featureless sphere of curved spacetime. Instead of an invisible ring surrounding the cabin, the source appeared in distinct modules, almost like engines attached to the sides of a vessel. The interior was designed to remain flat and free of shear, allowing clocks inside to remain synchronized and giving the passenger region a calm, habitable character. The strongest curvature could be moved toward the cylindrical walls and their end sections, while the number and placement of the nacelles could be adjusted to study different shapes. This was useful because engineering begins by breaking difficult systems into parts that can be examined separately. A continuous shell offers little freedom. A segmented arrangement allows researchers to ask how each region contributes to the total geometry. how the curvature changes when one nacelle is moved, and whether unwanted tidal effects can be reduced by smoothing the ends. But the nacelle model did not remove exotic energy. In the author's own calculations, the negative energy distribution was not eliminated. It was reorganized into separate cylindrical lobes. The new architecture made the strange source more localized and more adjustable, but not more available in nature. It gave the bubble a form that looked closer to a machine, while leaving the most difficult material question unresolved. A drawing can begin to resemble technology long before the required substance exists. And this is one of the quiet dangers of visually persuasive science. When a diagram has a cabin, walls, and engine-like structures, the mind naturally imagines bolts, cables, and construction, even though the objects in the diagram may represent mathematical stresses that no known material can produce. The 2025 nacelle study therefore belongs to the realm of improved geometry, not demonstrated propulsion. It showed that the wall of a warp bubble can be shaped in more than one way, that a calm interior can be maintained while the exterior source is broken into modules, and that the original spherical picture is not the only possible design. But it did not show how to build those modules or make the bubble travel faster than light. Then, in early 2026, the discussion moved from designing new bubbles to testing old ones more rigorously. A researcher introduced a computational tool called WARPAX, created to examine energy conditions from the viewpoints of many possible observers rather than from one convenient frame. This addressed a subtle weakness that had followed several positive energy claims. In relativity, two observers moving differently through the same region may divide what they measure into energy, pressure, and momentum in different ways. A bubble can appear physically acceptable to an observer traveling with the shell, while revealing negative energy or other violations to someone crossing it at another speed or angle. Earlier studies often tested a limited sample of observers because examining every possible motion is mathematically difficult. WARPAX approached the problem by searching continuously across the possible observer directions and velocities, asking where the most severe violations might be hiding. When it was applied to several well-known warp metrics, it found that checking only one preferred observer could miss violations across significant parts of the geometry or underestimate their severity by enormous amounts. The result did not prove that every future warp drive must fail, and it did not introduce a new law forbidding all unusual spacetimes. What it did was raise the standard of evidence. From that point forward, a model could no longer be called positive energy merely because one family of observers measured a favorable value. The full geometry had to be tested against a much broader range of motion. This made the field more demanding, but also more honest. A hidden weakness discovered by better analysis is not a step backward. It is knowledge replacing appearance. The ship in our imagined darkness had not moved, but the instruments examining its wall had become more sensitive. A few months later, another 2026 study addressed a problem that had remained almost untouched beneath many earlier designs: steering. A warp drive that can only exist at one constant velocity is not a useful vehicle. A real craft must change speed, turn toward a destination, correct its path, and eventually stop. The study asked whether a flat passenger region surrounded by positive energy matter could accelerate without relying on exotic material. Its answer was cautious but important. The researchers constructed a causal, sublight system in which the interior remained exactly flat while the exterior behaved like a photon rocket, losing mass by emitting radiation and gaining motion through recoil. In ordinary language, the system could steer because it threw energy away. The result preserved the familiar conservation laws rather than escaping them. Changing velocity required a payment, and the payment appeared as outgoing radiation and a reduction in the system's total mass. The model also placed limits on acceleration, showing that the larger and more compact the shell became, the more strongly its possible motion was constrained. This study made one point exceptionally clear. Curved space-time does not grant free propulsion. Even when the passenger region is protected and the energy remains positive, a vehicle must exchange momentum with something outside itself. A warp-like shell cannot simply decide to move because the geometry has been written that way. It must radiate, push, recoil, or interact with another physical system. Yet once again, the model stayed below the speed of light. The authors explicitly described it as causal, subluminal, and energetically costly. It provided a possible answer to how a positive energy warp-like structure might change velocity, but not how it could outrun light or create a global shortcut through space-time. Seen together, these recent studies form a pattern that is easy to miss when each result is presented alone. The closer warp research moves toward matter that behaves normally, causal control, stable interiors, and conservation of momentum, the more the resulting models tend to remain below the light speed boundary. The configurations that appear most physically respectable begin to resemble unusual gravitational vehicles rather than faster-than-light machines. Meanwhile, the models that preserve the dramatic promise of superluminal travel continue to face exotic energy, hidden violations, horizons, or unanswered questions about formation and control. This does not mean the newer work has failed. It means the field is learning to distinguish two ideas that were once blended together. One idea is a warp-like space-time, a moving shell or structured gravitational region carrying a protected interior. The other is a genuine superluminal shortcut, a path that reaches a destination before ordinary light traveling through the surrounding geometry. General relativity may allow the first under more ordinary conditions than once assumed. The second remains far more difficult. There is also a deeper value in the progression from 2024 to 2026. The 2024 study asked whether a positive energy shell could support a constant sublight warp geometry. The 2025 nacelle study asked whether the source could be divided into adjustable modules while preserving a flat interior. The early 2026 analysis asked whether claims about energy remained valid for every observer. The later 2026 steering model asked how motion could change without violating conservation laws. Each paper addressed a different missing piece, and none pretended to complete the whole machine. Together they reveal what a real theory of warp travel would need: a source that can exist, a geometry that remains stable, an interior that protects the passengers, a method for acceleration and navigation, an energy budget that closes, and a causal structure that does not prevent the crew from controlling their own vehicle. Faster-than-light motion would add another layer beyond all of these, one that the recent positive energy models have not crossed. So when we ask what has truly been discovered, the most accurate answer is not that humanity has found a road faster than light. We have found better ways to describe some of the terrain near that imagined road. We have learned that certain sublight warp geometries can satisfy familiar energy conditions, that bubble walls can be divided into structured regions, that energy must be tested from more than one observer's viewpoint, and that steering requires radiation, recoil, and a real physical cost. The progress is genuine, but it belongs to the science of curved space-time, not yet to interstellar transportation. The quiet ship remains at the center of the picture, surrounded now by a wall that is better mapped than before, but still not built. And even if future physics provides the matter and energy needed to shape that wall, the most difficult operational question will remain waiting in the darkness. Can the passengers inside create the bubble? communicate with its boundary, guide its path, and bring it safely to rest? Or would a truly superluminal structure become a vessel whose course lies beyond the reach of its own crew? Even if a future civilization discovered the matter, energy, and precision needed to shape a warp bubble, the existence of that bubble would still leave one of the most practical questions unanswered. Who controls it, and from where? A mathematical model can place a ship inside a perfectly formed region of curved space-time and allow that region to glide across the universe at a chosen speed. But a real voyage cannot begin in the middle of the story. The bubble must first be created around a vessel sitting in ordinary space. Its wall must grow from an initial state in which no special curvature exists. The energy supporting that wall must be transported into position, arranged with extreme accuracy, and changed smoothly enough that the forming geometry does not produce destructive tidal forces or intense bursts of radiation. Then the bubble must accelerate, follow a course, respond to corrections, and eventually slow down. Each stage is a different physical problem, and a solution describing steady motion does not automatically contain any of them. It is rather like being shown a calm photograph of a wave crossing the sea and being asked to infer the wind that created it, the energy that keeps it moving, and the method by which a sailor might persuade it to turn. The photograph may be exact, but the mechanism remains outside the frame. In many warp drive models, the location of the bubble is chosen in advance as part of the mathematics. The equations are told where the center will be at each moment, and the surrounding geometry is built around that prescribed path. This is useful for studying the shape of the space-time, yet it can create the illusion that the bubble possesses a propulsion system when the route has simply been written into the model from the beginning. A real spacecraft cannot rely on a path selected by the person writing the coordinates. It must carry or access some physical system that changes the energy and momentum of the surrounding fields. If the vessel is to accelerate toward another star, something must account for that acceleration. If it turns, the distribution of curvature must become asymmetric in a new direction. If it stops, the energy and momentum of the moving structure must be transferred somewhere else. General relativity does not erase conservation laws merely because the passengers rest inside a calm interior. The bubble, its wall, its energy source, and the ship together form one physical system, and the motion of that system must have a history that balances. Recent work on sublight warp-like shells has made this point clearer by showing that steering can be connected to radiation and recoil. A system may change velocity by emitting energy in one direction, much as a photon rocket moves by sending light the other way. This is far more physically understandable than a bubble that changes course without interacting with anything, but it also reveals the cost hidden behind the smooth geometry. Steering requires energy. Acceleration reduces the resources available to the craft. The faster or more massive the structure becomes, the greater the burden of changing its motion. Such models remain below the speed of light, where ordinary causal communication can still connect the center of the system to its surroundings. The superluminal case introduces a far stranger difficulty, because parts of the bubble wall may move beyond the reach of signals sent from the ship. Imagine standing in a quiet room while the front wall recedes in such a way that even a beam of light aimed toward it can never arrive. The room still surrounds you, and the wall still determines your motion, yet no command from your control panel can reach the place that must respond. This is not merely a delay caused by distance, it is a horizon, a boundary in the causal structure of space-time. Beyond it lie events that cannot be influenced from the interior, no matter how strong the transmitter or how long the crew waits. In an Alcubierre-style bubble traveling effectively faster than light, a forward horizon can appear because the leading region of the geometry is advancing relative to the interior too quickly for light emitted from the center to catch it. A rear horizon may also form, altering which signals can enter or leave the bubble from behind. The exact structure depends on the chosen geometry, but the general problem is severe. The crew may be carried by a space-time distortion that they cannot fully command. They could occupy the calm center, while the parts responsible for contraction ahead and expansion behind lie outside their causal control. A starship that cannot communicate with its own propulsion field would not behave like a vehicle in the ordinary sense. It would resemble a passenger cabin placed inside a route that must already know where it is going. This has led some researchers to suggest that the required space-time structure might need to be prepared in advance. Energy or field-generating equipment could be placed along the route before departure, forming a corridor through which the bubble later travels. But this solution weakens the dream it is meant to save. If a path to another star must first be built using slower-than-light methods, the warp system becomes less like a vessel exploring unknown space and more like a train moving along rails laid generations earlier. It might still shorten later journeys, but it would not allow immediate travel to an unprepared destination. Another possibility is that an external station creates and guides the bubble, controlling it from outside rather than relying on the crew. Yet the station would face its own causal limitations once the structure became superluminal, and any error in the predetermined path could be difficult or impossible to correct during flight. Even a tiny change in the destination, a moving planet, an unexpected object, or a failure in the supporting field might leave the occupants unable to intervene. The problem of starting the bubble is equally deep. To create a superluminal structure, the energy distribution around the ship must change from an ordinary configuration into one containing horizons and extreme curvature. In general relativity, not every finished space-time can arise smoothly from reasonable initial conditions. Some geometries can be written as complete mathematical objects, while remaining impossible to produce through any local process beginning in a normal region. The required source may need to appear in places that the ship cannot yet influence, or it may need to be arranged across an extended region before the bubble becomes active. If exotic energy is involved, the difficulty grows more severe, because the source must not only exist, but be transported and held in a pattern that may itself lie partly beyond ordinary causal reach. A real construction method would have to explain how every section of the wall receives its energy, how the timing is synchronized, and how the geometry avoids collapsing while it is only partially formed. During this transition, the passengers might be exposed to strong tidal gradients. A perfectly flat interior in the final design does not guarantee a gentle creation process. The walls of the bubble could move inward or outward, and small errors in their shape could produce differences in gravity across the vessel, stretching one region while compressing another. The larger the passenger compartment, the harder it may be to keep every part equally protected. The ship itself also contributes mass and energy. Simplified models sometimes treat the interior as empty or place a negligible test object at the center. But a real spacecraft would contain structure, fuel, instruments, people, and life support systems. Their gravity may be tiny compared with the proposed wall, yet a complete solution must include them. The total gravitational mass measured from far away must account for both the shell and its payload, and the interaction between them may alter the geometry that was designed under idealized assumptions. It is one thing to carry an almost weightless point through a curved spacetime. It is another to carry a vessel large enough for human life. Stopping the bubble may be even more dangerous than creating it. The curvature stored in the wall cannot simply vanish without consequence. If the supporting energy is removed, redistributed, or converted, the changing gravitational field may emit radiation. Particles and light encountered during the journey could also be affected by the bubble's geometry, becoming concentrated or shifted to higher energies near the leading wall. When the bubble slows or collapses, some of this accumulated energy might be released toward the destination. The severity of such effects depends on the precise model, and it would be misleading to treat every possible warp geometry as producing the same catastrophic outcome. But the risk illustrates a broader principle. A calm interior does not mean the entire system is calm. The passengers may experience a smooth voyage, while the exterior fields gather energy in ways they cannot see. Arrival is not merely the moment when the destination appears outside the window. It is a physical transition in which the distorted space-time must return to something close to its original state. That transition must preserve conservation laws, avoid destructive radiation, and place the ship on a normal, slower-than-light path relative to the destination. A bubble that cannot dissolve safely is not transportation. It is a moving region from which there may be no controlled exit. Navigation adds another layer. Stars and planets are not fixed points on a flat chart. They move through the galaxy, orbit within systems, and sit inside gravitational fields that curve space-time long before any engineered bubble arrives. A practical route would have to account for this existing geometry. The warp field would interact with the gravitational influence of stars, planets, dark matter, and perhaps interstellar gas. Tiny errors accumulated across light years could lead to enormous positional differences at arrival. Ordinary spacecraft correct their paths by observing their surroundings and adjusting their thrust. A superluminal bubble whose forward wall cannot receive signals from the crew may not possess that freedom. The course may have to be calculated with extraordinary accuracy before departure, turning navigation into a prediction of the future positions of every relevant object along the route. Even then, quantum uncertainty and unobserved debris would remain. These challenges do not prove that no future theory can provide a controllable shortcut. General relativity may eventually be understood as part of a deeper framework in which horizons, energy conditions, and quantum fields behave differently from current expectations. But within the physics we possess, the control problem is not a minor engineering detail to be solved after the energy source is discovered. It is woven into the causal structure of the proposed journey. The very feature that allows the bubble to beat ordinary light may prevent the passengers from commanding it. The farther the geometry departs from ordinary sublight motion, the more the vehicle begins to resemble a path imposed upon space-time rather than a ship choosing its own course. And so, the silent cabin remains suspended inside our imagined bubble, its lights dim, its clocks moving gently forward, while beyond the windows the surrounding wall performs the impossible work of the voyage. The passengers may know where they wish to go, but desire cannot cross a horizon. Their instruments may calculate a correction, but a calculation cannot steer a region that no signal can reach. Before a warp drive could become a true vehicle, physics would need to explain not only how space-time can be shaped, but how that shape can listen, respond, and safely return control to those traveling within it. And even if that problem were solved, the bubble would still have to survive something more restless than any crew or engine: the quantum vacuum surrounding every point of its journey. The quantum vacuum is often imagined as the deepest possible emptiness, a perfectly dark stage left behind after every particle, atom, and ray of light has been removed. Yet modern physics describes something far less silent, because even the lowest energy state of a field is not a motionless nothing. It contains fluctuations, correlations, and possibilities that normally remain too small and too balanced to disturb the calm appearance of empty space, but a powerful gravitational geometry can alter that balance, separating modes that were once harmless shifting their frequencies and allowing the vacuum to respond as though the space-time itself had become an instrument drawing energy from invisible strings. A warp bubble may look smooth and stable when examined only through classical general relativity, the theory in which space-time curves continuously in response to matter and energy. But the universe is also filled with quantum fields, and every electron, photon, and other known particle is understood as an excitation of those fields. If the bubble contains horizons, steep gradients, or rapidly changing curvature, the quantum state around it may no longer remain quiet. This is why a geometry that appears elegant on paper must eventually face a more difficult question. What happens when the vacuum notices it? Physicists do not yet possess a complete theory of quantum gravity, so they often begin with an intermediate approach called section-mammable gravity. In this approximation, space-time itself is still treated using Einstein's theory, while matter and radiation are described quantum mechanically. The average energy produced by the quantum fields is then allowed to curve space-time in return. This response is called backreaction, and it matters because the bubble cannot remain an unmoving background while the fields around it accumulate energy. If the quantum vacuum creates a large concentration near the wall, that concentration becomes a new gravitational source. It may distort the geometry that produced it, strengthening some regions, weakening others, or causing the entire structure to lose stability. A warp bubble may therefore fail not because the classical equations were wrong, but because the solution ignored the physical reaction of the fields living inside those equations. The closest natural comparison is a black hole, although the two geometries are not identical. Near a black hole horizon, quantum fields can be divided differently by observers on opposite sides of the causal boundary, and this difference is associated with Hawking radiation. A black hole that appears perfectly dark in classical relativity may emit an extraordinarily faint thermal glow once quantum effects are considered. A superluminal warp bubble can also contain horizon-like boundaries, particularly at the front and rear of the moving region, and these boundaries may produce related effects. An observer inside the bubble could detect a bath of particles or radiation whose effective temperature depends on the geometry and acceleration of the wall. In some idealized calculations, this temperature becomes dangerously large for rapid superluminal motion. The exact prediction depends on the shape of the bubble and on assumptions about the quantum state, so it would be unwise to treat one result as a final description of every possible warp geometry. But the general lesson is difficult to avoid. Horizons are not passive lines. They change how fields are divided into particles and vacuum, and that division can carry real energy. The front wall presents an especially troubling problem. Light and other field disturbances traveling toward it may be repeatedly shifted to shorter wavelengths. Shorter wavelengths correspond to higher frequencies and greater energy, a process known as blue shifting. In an ordinary setting, a single blue shift may be modest, like the change in pitch heard when a sound source approaches. Near certain horizons, however, modes can be compressed again and again, creating what is sometimes called an infinite blue shift problem in an idealized limit. A field fluctuation that began with almost no detectable energy may become violently energetic when traced toward the horizon. Earlier Assad studies of simplified warp drive models found that the energy measured near the leading wall could grow with time, suggesting that a superluminal bubble might become unstable soon after it formed. The vacuum would not merely warm the cabin, it could build an increasingly intense layer of energy near the front of the geometry, and that energy would then push back against the space-time, threatening the shape of the bubble itself. The image is strange, but gentle enough to hold in the mind. a silent vessel moving through darkness while an invisible brightness gathers along its forward edge, not because the ship strikes physical air, but because the vacuum has been compressed by the causal structure of the journey. This has sometimes been described as a decisive argument against warp drives. Yet the scientific picture is more careful. Many early calculations were performed in one spatial dimension plus time, a simplified world in which the bubble moves along a line and many features of real three-dimensional space are absent. Such models are valuable because they reveal mechanisms that might otherwise be hidden inside overwhelming mathematics, but they can also exaggerate effects by forcing every field mode toward the same narrow region. In three spatial dimensions, light and quantum disturbances can approach the bubble from different directions, travel around parts of the wall, or concentrate only at particular points rather than across an entire surface. Later work has suggested that the most severe blue shifts may depend strongly on the detailed geometry, including the thickness and shape of the wall, the direction of motion, and the way the bubble interacts with incoming radiation. Some researchers have compared this sensitivity to aerodynamics, not because the bubble moves through a material atmosphere, but because its shape may determine how fields flow around it. A blunt front could collect disturbances differently from a smooth or elongated one. A carefully chosen wall might spread some of the energy across a wider region, while another shape might focus it into a dangerous point. This possibility does not remove the quantum problem, but it changes it from one universal sentence into a difficult design question. No known shape has been shown to make a macroscopic faster-than-light bubble fully stable. Yet neither has every imaginable geometry been ruled out by a single calculation. Another complication comes from the particles and radiation already present in interstellar space. The space between stars is extremely thin, but it is not perfectly empty. It contains stray atoms, dust grains, cosmic rays, low-energy photons, and the faint microwave background left from the early universe. As a warp bubble travels, these particles may encounter its curved wall. Their paths could bend, their energies could shift, and some could become trapped or carried near the front. If the bubble later slows down, changes shape, or collapses, the accumulated material might be released in a concentrated burst. Popular discussions sometimes describe this as an unavoidable explosion capable of destroying the destination. But the actual outcome depends on how particles interact with the specific geometry, whether they truly remain trapped, how long the journey lasts, and how the bubble is brought to rest. The risk should be treated as an unresolved physical concern rather than a certain cinematic catastrophe. Still, it reveals a truth that appears repeatedly in warp drive research. Arrival cannot be separated from travel. Anything gathered, shifted, or stored by the wall during the journey must eventually be accounted for. The bubble may protect the passengers from direct collision while transferring the danger to the moment of collapse. Even if no large quantity of external matter accumulates, the changing geometry itself can radiate. General relativity predicts that accelerating masses and changing patterns of curvature may produce gravitational waves, ripples that travel outward through space-time. Researchers have numerically explored what might happen if a hypothetical warp bubble became unstable and collapsed, calculating the possible gravitational waveform released during the event. These studies are not evidence that warp bubbles exist in nature. They are controlled experiments performed inside mathematics, asking how Einstein's equations behave when an unusual configuration is disturbed. Their value lies in showing that the death of a bubble would not necessarily be quiet. A portion of the energy stored in the geometry could escape as gravitational radiation, while the remaining fields settled into a more ordinary state. If such an event occurred in the real universe, the signal might carry information about the bubble's size, wall thickness, and manner of collapse, much as gravitational waves from merging black holes reveal the properties of the objects that produced them. For now, however, these waveforms remain predictions from hypothetical initial conditions, not signs of an undiscovered civilization. There is also a deeper tension between the energy needed to create the bubble and the quantum restrictions discussed earlier. Negative energy may be permitted locally, but quantum theory appears to limit its magnitude and duration. Making the wall thinner can reduce the total exotic energy in some classical estimates, yet a thinner wall creates sharper gradients, and sharper gradients excite shorter wavelength quantum modes. The attempt to reduce one difficulty may therefore strengthen another. If negative energy is compressed into a very narrow layer, the required quantum state may become increasingly difficult to sustain, while the curvature may approach scales where the secession carnival approximation itself breaks down. At that point, physicists would need a true theory of quantum gravity, one capable of describing spacetime and quantum fields as parts of a single system rather than placing one on top of the other. No experimentally confirmed theory currently provides that complete description. Approaches such as string theory, loop quantum gravity, and other programs offer possible frameworks, but none has yet produced a tested blueprint for a stable macroscopic shortcut. This leaves warp drive research in an unusual position. The classical equations can be explored with great precision, while the quantum regime most likely to decide the bubble's fate remains incomplete. The absence of a final theory should not be used as permission to assume that future physics will rescue every desirable geometry. Unknown physics may open possibilities, but it may also impose stronger restrictions. Nature has often proved more subtle than earlier theories, though not always more generous. Quantum mechanics allowed effects classical physics could not imagine, yet it also introduced uncertainty, vacuum fluctuations, and limits on measurement. A future theory of gravity might reveal new states capable of supporting unusual curvature, or it might show that causal shortcuts are excluded by a principle deeper than the energy conditions now understood. Until such a theory is tested, the responsible conclusion remains suspended between possibility and evidence. We cannot say that every warp bubble is absolutely forbidden, but we also have no reason to believe the quantum vacuum will allow one to pass peacefully at superluminal speed. The imagined ship continues to drift within its calm interior, and from the passenger's point of view, the cabin may still appear untouched. Their instruments show no violent acceleration. Their clocks advance gently. Yet just beyond the wall, quantum fields are being stretched, divided, and shifted by a geometry unlike anything naturally observed. A faint fluctuation may become a particle. A harmless wavelength may be compressed into dangerous radiation. Energy may gather near a horizon that the crew cannot reach, while the resulting back reaction begins to reshape the bubble carrying them. The true challenge is no longer simply to create a curved region, but to create one that remains self-consistent when every field in the universe is allowed to answer back. And if the vacuum refuses to remain silent, then the most beautiful classical shortcut may last only for a moment before dissolving into radiation and ordinary spacetime, leaving us to search for other proposed paths: wormholes, hypothetical faster-than-light particles, quantum tunneling, and entanglement, to discover whether any of them can carry matter or information where a normal beam of light cannot yet go. When the warp bubble begins to look too fragile, too costly, or too difficult to control, the mind naturally turns toward other doors, other ways the universe might allow a traveler to reach a distant place before ordinary light could complete the same journey. And among these possibilities, 4 ideas return again and again: wormholes, tachyons, quantum tunneling, and entanglement. Each of them is real in a different sense. Some are legitimate mathematical solutions, some are speculative particles, and some are experimental confirmed quantum effects. Yet none has shown that a person, an object, or a chosen message can be sent beyond the ordinary causal boundary established by light. Wormholes are perhaps the closest relatives of warp drives because they do not ask a traveler to move locally faster than light. Instead, they change the route itself. Imagine two distant points on a sheet of paper. If the sheet remains flat, the shortest path lies across its surface. But if the sheet is gently folded until the 2 points nearly touch, a narrow tunnel between them could connect locations that were once far apart. The paper is only a metaphor, because real space-time is not known to be folded through a larger room. But the image captures the essential idea. A wormhole would create a shorter path through geometry rather than a greater speed through local space. Einstein's equations contain structures related to wormholes. In 1935, Albert Einstein and Nathan Rosen studied a bridge connecting different regions of a space-time associated with an idealized black hole. This Einstein-Rosen bridge was not a passage a traveler could safely cross. It closed too quickly and was hidden behind horizons, so anyone attempting to enter would not emerge through the other side, as though walking through a tunnel. Decades later, physicists explored whether a different geometry might remain open long enough for matter to pass through. A traversable wormhole would need a throat, with no event horizon blocking the path, and no singularity destroying the traveler. The route through the interior could be short, even if the two mouths were separated by many light years in ordinary space. A ship moving gently through the throat might emerge at the far mouth long before a beam of light following the external route arrived. From inside the tunnel, the ship would never need to exceed the local speed of light. Globally, however, the journey would function as a true shortcut. The difficulty appears at the throat. Ordinary positive energy matter tends to make gravity pull inward and focus paths together. A wormhole throat must resist collapse and remain open, which usually requires the geometry to curve in the opposite way. In the standard analyses of general relativity, this behavior is connected with violations of familiar energy conditions, and therefore with exotic forms of stress or negative energy. The problem resembles the wall of a warp bubble. Quantum physics permits limited negative energy effects, but no experiment has shown how to produce a stable, human-sized throat or sustain it for the duration of a voyage. Even if a tiny wormhole could somehow appear as a quantum fluctuation, enlarging it without collapse would be a separate challenge, and feeding ordinary matter into it might disturb the delicate geometry enough to close the passage. A traveler would also need to know where the other mouth leads. A wormhole does not automatically open beside a chosen star. Its mouths would need to be created, discovered, or transported into position, and moving one mouth to a distant destination by slower-than-light means could take the very centuries the shortcut was intended to avoid. The geometry also touches the problem of time. If one mouth traveled at high speed or remained in a stronger gravitational field, its clock could fall out of step with the clock at the other mouth. Passing through the tunnel might then connect not only different places, but different times. Under some arrangements, a traveler could return to the original region before departure, creating a closed path through time. This is one reason wormholes are not merely tunnels waiting for stronger materials. Their existence would reach into the foundations of causality. Another proposal, known as a Krasnikov tube, also attempts to create a shortened route through space-time. In the original idea, a spacecraft first travels toward a distant star at ordinary sublight speed, altering the geometry along its path. Once the tube has been prepared, the return journey, or later journeys through the same corridor, could take far less time as measured by clocks near the starting point. The first voyage would still be slow, and the route would have to be built before it became useful. Like warp bubbles and wormholes, the tube appears to require unusual energy distributions, and suitable arrangements of multiple tubes may lead to causal loops. It therefore offers an illuminating mathematical example of a prepared spacetime shortcut, but not an established transportation system. Tachyons approach the problem from a completely different direction. Instead of changing the geometry, they are hypothetical entities that would always move faster than light. They would not begin as ordinary particles, accelerate toward the light barrier, and cross it. Relativity separates slower than light and faster than light paths into different classes, so a tachyon would be born on the superluminal side and could never slow down to the speed of light. Curiously, in the simplest formulas, adding energy to such a particle would reduce its speed toward the light boundary, while removing energy would make it move even faster. These strange properties are mathematically interesting, but no tachyon has ever been detected. The word tachyon also appears in quantum field theory, where a field may be described as having a tachyonic mass term. This usually does not mean that faster-than-light particles are flying through the laboratory. It more often means that the assumed state of the field is unstable, like a ball balanced at the top of a hill. The field then rolls toward a more stable state, and the apparent tachyon disappears from the final physical description. This distinction is important because headlines sometimes treat every tachyonic equation as evidence for superluminal matter. In many cases, it signals instability rather than travel. Even if stable tachyons existed, communication with them would create serious causal difficulties. Different observers could disagree about the order in which a tachyon was emitted and received. With suitable relative motion and a return signal, a message might arrive before it was sent. Some theoretical approaches attempt to restrict interactions or choose a preferred frame to avoid such loops, but these changes would alter the symmetry that lies at the heart of relativity, and no evidence currently requires such a revision. Quantum tunneling offers a more experimentally grounded source of apparent superluminal behavior. A quantum particle is not represented only as a tiny object following one exact path. It is described by a wave-like distribution of possibilities. When this quantum wave reaches a barrier that the particle lacks enough classical energy to cross, part of the wave may extend through the barrier, allowing the particle to be detected on the other side. The effect is real and essential to modern technology and natural processes. It contributes to radioactive decay, nuclear fusion inside stars, and the operation of scanning tunneling microscopes. Experiments measuring how long tunneling appears to take have sometimes produced remarkably short delays. In certain arrangements, the front edge carrying genuinely unpredictable information remains constrained by causality. Entanglement may be the most mysterious of all because it produces correlations between distant systems that have no simple classical explanation. Two particles can be prepared in a shared quantum state so that measurements performed far apart reveal related outcomes. Experiments testing Bell's inequalities have repeatedly shown that these correlations cannot be explained by a simple model in which each particle carried a complete set of hidden local instructions from the beginning. The result is genuinely non-classical. Yet entanglement does not operate like an invisible telegraph. When one observer measures their particle, the outcome is individually random. They cannot choose whether the detector reports one result or another, and therefore cannot use the result to encode a deliberate message. The distant observer also sees a random sequence. The hidden correlation becomes visible only when the two observers later compare their records through an ordinary communication channel, which remains limited by light. Quantum teleportation follows the same rule. Despite its dramatic name, it does not make an object disappear in one place and immediately reappear elsewhere. It transfers the quantum state of a system using previously shared entanglement together with classical information that must travel at or below the speed of light. The original local state is destroyed during the process, and the distant reconstruction cannot be completed until the classical message arrives. Entanglement therefore challenges ordinary ideas about separateness, but it does not provide controllable superluminal signaling. There are also theoretical ideas involving exotic quantum arrangements, curved spacetime, or connections between entanglement and wormhole-like geometry. These possibilities are active areas of research, especially in attempts to understand quantum gravity. Yet they have not produced a traversable channel through our universe or a method of moving information faster than light. The connection may reveal something profound about how space-time emerges from quantum relationships, but a deep structural resemblance is not the same as a usable passage. When all these alternatives are placed beside one another, a quiet pattern appears. Wormholes and Krasnikov tubes can shorten global routes, but they require geometries whose material support and stability remain unknown. Tachyons could move beyond the light boundary by definition, but no evidence shows that stable tachyonic particles exist, and their interactions threaten causality. Quantum tunneling produces unusual timing, but not verified superluminal messages. Entanglement creates correlations across distance, but not a channel through which an observer can choose what the other receives. Each idea reaches toward one part of the dream, while leaving another part untouched. Some offer mathematical permission without physical matter. Some offer experimentally confirmed strangeness without controllable communication. Some preserve local relativity but demand extraordinary global geometry. None has passed through all the doors required of a real faster-than-light method. A consistent theory, a realizable source, a controllable mechanism, and experimental evidence that matter or chosen information has reached beyond the ordinary future defined by light. And perhaps this repeated failure is pointing towards something deeper than an unfinished engine. Because every serious route toward faster-than-light travel eventually approaches the same boundary. Not merely the boundary of speed, but the boundary between cause and effect, where a shortcut through space may quietly become a path into the past. The deepest obstacle to faster-than-light travel may not be energy, engineering, or even the strange behavior of the quantum vacuum, but something quieter and more fundamental: the order in which events are allowed to happen. In ordinary life, causality feels so natural that we rarely notice it. A hand releases a glass, and only afterward does the glass fall. A star collapses, and only later does its light reach a distant telescope. A message is written before it is received. This simple sequence gives the universe a readable history, a direction in which explanations can be followed backward from effects to causes. Relativity preserves this order for every pair of events that can be connected by light or by anything moving more slowly than light. Observers may disagree about how much time passes between those events, and they may disagree about the distance separating them, but if one event causes the other, they agree about which came first. The trouble begins when two events are separated so widely in space and so closely in time that even light cannot travel between them. Such events lie outside one another's ordinary causal reach, and relativity allows different observers to disagree about their order. One observer may say that event A happened before event B, while another observer, moving relative to the first, may say that B happened before A. This does not create a contradiction, because no message can normally pass between them. Neither event can cause the other, so their order does not need to be universal. They are like two distant flashes seen from moving trains, with no physical thread connecting one flash to the next. But a true faster-than-light signal would create exactly such a thread. It would connect events that ordinary light cannot connect, and once that connection exists, the disagreement about their order becomes more than a matter of perspective. It begins to threaten the distinction between sending and receiving. Imagine two observers, Eleanor and Marcus, moving steadily relative to one another through deep space. Eleanor sends Marcus a faster-than-light message. In Eleanor's frame, the sequence seems perfectly sensible. She writes the message, transmits it, and Marcus receives it later. Yet because the transmission crosses a separation outside the ordinary light cone, Marcus may describe the same events differently. In his frame, the message may arrive before Eleanor sent it. This alone does not yet create a complete paradox because Marcus could simply receive a message whose sending lies in what Eleanor calls the future. The true difficulty appears when Marcus replies using the same kind of superluminal method. His return signal can travel along another path outside the light cone, and with the right relative motion, it may reach Eleanor before she transmitted the original message. She could receive a reply to words she has not yet written. This arrangement is sometimes called a tachyonic antitelephone, although it does not require actual tachyon particles. Any controllable signaling method that moves outside the ordinary causal cone could produce the same structure if the laws remain symmetric for observers in relative motion. No one needs to travel at an impossible speed in their own immediate surroundings. The paradox emerges from combining superluminal communication with the relativity of simultaneity. The order of distant events shifts between frames, and two carefully arranged signals can close the path into a loop. Elena might receive Marcus's warning telling her not to send the original message. If she obeys, Marcus never receives it and therefore never sends the warning. If she ignores the warning, the loop remains, but the origin of the information becomes unclear. A message could circulate through time without ever being created in the ordinary sense, copied from its own future and returned to its own past. Such stories are familiar in science fiction, but their roots are not merely literary. They grow from the geometry of space-time, and from the way different observers divide that geometry into space and time. The difficulty cannot be removed simply by saying that everyone involved personally experiences time moving forward. Eleanor's clock always advances. Marcus's clock also advances. Each signal moves from emission to reception along its own proposed path. Yet the combined network of paths may return information to an earlier event in Eleanor's history. Locally, every participant moves toward their future. Globally, the route bends through space-time and arrives in the past. This is one reason faster-than-light travel and time travel are so closely linked in relativity. A shortcut across space can become a shortcut across time when viewed from another state of motion. Warp drives face this problem, even though the passengers inside a single bubble might never feel themselves moving backward in time. One isolated trip from Earth to a distant star does not automatically form a time machine. The ship may depart, cross the engineered geometry, and arrive while all clocks aboard continue normally. But if two warp journeys are arranged in different directions, or if the departure and arrival systems move relative to one another, their combined paths may form what physicists call a closed time-like curve. This is a route through space-time that eventually returns a traveler to an event in their own past, while the traveler always moves forward according to the clock they carry. The phrase sounds contradictory only because everyday space does not contain such paths. In curved space-time, however, the global arrangement can be stranger than the experience along any small part of the route. The traveler never turns around within time, as though walking backward through a corridor. The corridor itself bends until its future end meets its past beginning. Mathematical studies have shown that properly arranged warp-like regions can, in principle, create this kind of loop. The result does not prove that warp drives exist, but it shows that if superluminal bubbles were physically available, using them without disturbing causality might be far more difficult than simply choosing responsible destinations. Wormholes carry the same danger in an even more intuitive form. Suppose a traversable wormhole has two mouths, initially resting near each other with synchronized clocks. One mouth is then carried on a high-speed journey and returned, or placed for a long time in a stronger gravitational field. Relativity tells us that the two mouths can accumulate different amounts of elapsed time. From the outside, their clocks no longer agree. Yet the short path through the wormhole might continue to connect them almost directly. Entering the younger mouth could allow a traveler to emerge from the older mouth at a time earlier than the external journey would permit. If the mouths are arranged carefully, the traveler could then move through ordinary space and return to the starting point before entering the wormhole. A tunnel through space would have become a machine connecting different moments. Once again, the traveler does not locally exceed light inside the throat. The causal loop arises from the global relationship between the mouths, their motion, and their gravitational histories. This is why the problem cannot be dismissed by repeating that a warp ship or wormhole traveler always moves below light speed nearby. Local obedience does not guarantee global innocence. A geometry can respect the light speed limit in every small region while joining those regions in a way that allows a return to the past. General relativity itself contains several mathematical spacetimes with closed time-like curves. Some involve rotating universes, infinitely long spinning cylinders, or the internal geometry of idealized rotating black holes. These examples do not show that nature creates accessible time machines. Many rely on unrealistic conditions, infinite structures, unstable regions, or parts of spacetime hidden behind horizons. Their importance is more conceptual. Einstein's equations alone do not automatically remove every causal loop. Additional physical principles may be needed to explain why the universe we observe appears to protect a consistent history. Stephen Hawking proposed the idea of chronology protection, suggesting that the laws of physics may prevent closed time-like curves from forming on macroscopic scales. In some calculations, quantum fields grow violently near the boundary where a time machine would first appear. The accumulating energy might curve spacetime strongly enough to destroy the developing loop before it becomes usable. This resembles the quantum instability feared near warp horizons. The vacuum reacts to the attempted causal structure and may prevent the geometry from remaining calm. Yet, chronology protection has not been established as a universal theorem. Semi-classical calculations become unreliable precisely when the quantum back reaction becomes extremely large, and without a complete theory of quantum gravity, the final outcome remains uncertain. Some models appear to avoid immediate divergence under special assumptions, while others suggest that causal violations are unstable or inaccessible. The responsible conclusion is not that time machines are certainly possible, nor that a proven mechanism absolutely forbids them, but that causality places severe constraints on any proposed superluminal method. There are several ways a future theory might try to preserve order. It could forbid all controllable signals outside local light cones. It could allow unusual correlations, but prevent them from carrying chosen information, as quantum entanglement does. It could introduce a preferred cosmic frame, allowing superluminal motion only in one special definition of time and thereby blocking the return paths needed for paradoxes. But a preferred frame would modify the symmetry at the foundation of special relativity, and no compelling experimental evidence has yet shown that such a frame exists. A theory could also enforce self-consistency, allowing causal loops only when every event fits together without contradiction. Eleanor might receive a warning from the future, but every attempt to avoid sending the original message would somehow become part of the circumstances that cause her to send it. This approach removes logical inconsistency, yet it raises difficult questions about choice, probability, and the origin of information. Another possibility is that history branches. with a traveler entering a different future rather than changing the past from which they departed. Such ideas appear in interpretations of quantum mechanics and speculative models of spacetime, but they have not been established as descriptions of real macroscopic time travel. What remains firm is the connection. A controllable road faster than light cannot be considered only as transportation. It is also a proposal about the structure of time. The speed of light protects more than a limit on engines. It separates events whose order must be shared by every observer from events whose order can depend on motion. As long as information remains inside the light cone, these differences fit together without contradiction. Causes remain before their effects for everyone who can be connected to them. The moment a signal is allowed to step outside that cone, the quiet agreement begins to unravel. And so the imagined warp ship now carries a burden more delicate than its energy shell. It must not only cross the darkness between stars, it must cross without folding its own departure into its arrival. Its passengers may see their destination ahead, calm and waiting, while somewhere in another frame, the journey is already moving toward yesterday. Perhaps a deeper law prevents that path from closing. Perhaps quantum gravity protects the order of events in a way we do not yet understand. Or perhaps every real method of superluminal travel would arrive with time travel hidden inside it, inseparable from the shortcut that made the journey possible. After all the mathematics, energy, horizons, and quantum fields, we are left with a boundary that feels almost philosophical but remains entirely physical. The universe may resist faster than light travel, because it is preserving the minimum order required for anything to have a history at all. After traveling through the limits of motion, the geometry of space-time, the strange demands of energy, the difficulty of steering a warp bubble, the response of the quantum vacuum, and the fragile order of cause and effect, we can finally return to the question that began this journey and answer it without mystery. No, humanity has not yet discovered a real way to travel faster than light. We have discovered equations that describe unusual paths through space-time, models that reveal how a quiet region might be carried inside a shell of curvature, and sublight configurations that appear more physically reasonable than the earliest warp drive proposals. But we have not built a working system, created a verified bubble, or sent matter or information beyond the ordinary reach of light. The distance between a mathematical possibility and a real method of travel remains immense. And the clearest way to understand that distance is to imagine 4 doors standing between an elegant idea and a functioning starship. The first door is mathematics, and this door has opened part way. General relativity allows space-time to bend, stretch, expand, form horizons, and connect distant regions in ways that ordinary intuition would never predict. The Alcubierre bubble, traversable wormhole models, Krasnikov corridors, and later warp geometries all show that Einstein's equations contain structures capable of shortening a global route without requiring a traveler to outrun nearby light. These structures are not meaningless fantasies. They are serious mathematical laboratories in which physicists test the limits of gravity, causality, and energy. A valid solution can reveal that the equations do not immediately forbid a certain shape of spacetime. It can show where curvature must gather, how clocks behave inside the structure, and what a distant observer might measure. It can even expose hidden relationships between gravitational geometry and the movement of information. Yet, mathematics alone does not decide whether nature can create the solution. Einstein's equations contain black holes, and the universe has shown us black holes. They also contain idealized universes with properties that may never have existed. The equations describe possibilities under chosen assumptions, and a warp metric begins by choosing the geometry one hopes to obtain. It then asks what kind of physical source would be needed to support it. This leads to the second door, the door of matter and energy, which remains closed for genuine faster-than-light travel. Some modern models have shown that a warp-like shell moving below the speed of light may be supported by positive energy and may preserve a calm interior. This is important because it proves that not every geometry called a warp drive must depend on obviously exotic material. A structured gravitational shell can, in principle, exist on the slower side of the light barrier, while obeying familiar energy requirements. But when the model is asked to create a true global shortcut, allowing arrival before ordinary light traveling through the surrounding space, the old difficulties return. Negative energy may appear near the wall. Familiar energy conditions may fail for some observers. Pressures and tensions may become more extreme than any known material could survive. Even when the total energy is positive, the local distribution may still contain regions no known field can produce. Positive energy is not automatically practical energy. A neutron star contains positive energy, but no civilization knows how to gather and shape a neutron star around a spacecraft. A black hole has positive mass, yet its gravity is not a gentle tool that can be arranged into a moving cabin. The required source must not only exist, it must be created in the correct shape, held stable, moved with the vessel, and changed whenever the course changes. Quantum theory permits small and temporary negative energy effects, but it has not provided a reservoir large enough to support a human-scale shortcut. Known restrictions suggest that stronger negative energy can generally be sustained only for shorter periods or within smaller regions. The universe appears to allow tiny departures from ordinary energy behavior while resisting their expansion into permanent macroscopic structures. Perhaps a deeper theory will reveal new states of matter, but no verified theory or experiment currently supplies the material needed for a superluminal bubble or traversable wormhole. The third door is formation and control, and this door has not opened either. Most warp drive calculations begin with the desired geometry already present. The bubble exists, the wall has the correct shape, and the center moves along a chosen path. A real spacecraft would have to create that condition from ordinary space. The supporting energy would need to arrive at every part of the wall. The structure would need to form without producing lethal tides or radiation. It would need to accelerate without violating conservation of momentum, turn toward a destination, correct its path, and slow down safely. Recent sublight models have made the cost of steering clearer by connecting acceleration to radiation and recoil. The system must release energy or exchange momentum with something outside itself. Curved spacetime does not grant motion for free. In the superluminal case, control becomes even more difficult because horizons may prevent signals from the passengers from reaching parts of the bubble wall. The region responsible for shortening the space ahead could lie outside the crew's causal reach. A command may be sent forward and never arrive. The ship could be carried by a geometry that it cannot fully influence, like a cabin trapped inside a wave whose leading edge cannot hear the helm. The route might need to be prepared in advance, perhaps by equipment placed across interstellar space before the voyage begins. Such a system could still be useful to a distant future civilization, but it would no longer be a free-moving craft capable of choosing an unexplored star and leaving at once. It would resemble a cosmic railway, valuable only after the path had already been built by slower means. Stopping presents its own dangers. Energy stored in the wall must be redistributed. Radiation and particles affected during the journey must go somewhere. The bubble must return to ordinary spacetime without releasing a destructive burst toward the destination or leaving the ship stranded inside a collapsing geometry. No current model gives a complete tested history from creation to acceleration, navigation, arrival, and safe shutdown for a faster-than-light vehicle. The fourth door is experiment, and here the answer is simplest. It remains completely closed. No laboratory has created a confirmed warp bubble. No traversable wormhole has been observed. No stable tachyon has been detected. No experiment has sent a freely chosen message outside its future light cone. Quantum tunneling has produced unusual timing, but not controllable faster-than-light communication. Entanglement has revealed correlations that defy classical explanation, but those correlations cannot be used to send a deliberate message without an ordinary, slower-than-light channel. Apparent superluminal motion in astronomy, fast-moving patterns, and expanding cosmic distances do not carry local matter beyond light. The scientific standard is not whether an effect looks fast, sounds strange, or produces a number larger than the speed of light in a particular coordinate system. The standard is whether matter or new information reaches an event that ordinary light could not yet reach, and whether the result can be measured, repeated, and independently verified. Nothing has passed that test. This does not mean research on warp drives has been wasted. The value of the subject lies partly in what it reveals about the laws we already possess. Warp geometries force physicists to examine the meaning of energy in different frames. They expose the difference between a completed spacetime and a process that can actually create it. They show how local obedience to the light speed limit can still produce global threats to causality. They connect gravity with quantum fields and reveal how horizons may turn vacuum fluctuations into real radiation. They help develop numerical tools that can also be applied to black holes, gravitational waves, cosmology, and other extreme environments. A question can be scientifically valuable even when the desired machine remains impossible to build. Sometimes the attempt to open one door illuminates the entire structure of the house. What, then, would count as a true discovery? It would not be another drawing of a bubble or another coordinate path that crosses a distant map quickly. A genuine breakthrough would need to identify a physically realizable source of curvature, show that the source remains stable, and demonstrate how it can be created from ordinary initial conditions. It would need to provide a complete method of acceleration, steering, and shutdown. It would have to survive quantum back reaction and avoid dangerous horizons or explain how they can be controlled. It would need to preserve causality or offer a deeper, experimentally supported principle explaining why causal loops do not arise. Most importantly, it would need evidence. A measured space-time distortion, a signal arriving beyond the normal causal boundary, and independent repetition by other researchers. Until something of that scale occurs, claims that humanity has discovered faster-than-light travel should be treated as exaggerations of interesting theoretical work. The honest verdict is therefore both firm and gentle. We have not found the road. We have found several sketches of what such a road might look like. We have learned that the ship cannot simply accelerate harder. We have learned that changing the route may be more promising than changing the local speed. We have learned that geometry carries a physical price, that the price may involve unusual matter, that control may be blocked by the same horizons that make the shortcut possible, and that a journey across space may quietly become a journey toward the past. The deeper we look, the less warp travel resembles an advanced version of rocketry, and the more it resembles an attempt to rewrite the relationships between distance, time, and cause. Perhaps future physics will discover principles that our current theories cannot see. Perhaps space-time emerges from a deeper quantum structure that allows shortcuts under conditions not yet imagined. Or perhaps the light-speed boundary will survive every new theory, not as a temporary limit of technology, but as part of the logic that keeps the universe consistent. Science cannot choose the answer in advance. It can only follow evidence, refine the questions, and resist the temptation to mistake possibility for discovery. And so the imagined ship remains where we first found it, resting quietly between distant stars. No engine burns behind it. No bubble glows around its hull. The distance ahead remains measured in years of light. Yet the journey has not been empty, because the darkness around the vessel is no longer shapeless. We can now see the walls that surround the dream, the local boundary of light, the energy hidden inside curvature, the horizon beyond the pilot's reach, the restless vacuum, and the delicate thread of causality holding every event in order. We have not discovered how to cross those walls, but we understand them more clearly than before. And sometimes, long before the universe offers a door, it first teaches us to recognize the wall. We may not have found a true path beyond light, but each question brings us closer to understanding the universe. Thank you for listening, and please subscribe to Sleepy Space for more peaceful cosmic journeys.